to join, it's a free session. And then I'll move out. Okay, hello everybody. This is Mitesh here. Good to see you all again. And today here we are with Santosh Nimkar sir, a veteran teacher, profound teacher of physics. In fact, I would say the best teacher for physics. Okay, that I have ever seen. And the amount of time and patience he has is much enormous, much better than what I have. Clearly, I can say that. Yeah, the amount of time that he invests in teaching you all, I'm sure you kids also will be convinced with what I am saying. So today, guys, we are having physics live session, free session on YouTube as well. Anyone out over there on the YouTube channel, if you want to join and if you want to study physics with us, yes, this is the time you can do that for sure. The link is being pasted over there. Samir sir, are you pasting the link on the YouTube as well?
Yes, sir.
Okay. So we are pasting the link over there also, guys. You can join with us completely free for today's session. And sir is going to teach you refraction of light at plane surfaces. Am I right, sir?
Absolutely, absolutely.
Chalo, at least I know something in physics. At least the topic correctly. Okay. So boys and girls, we are getting you the best teacher, and trust me, he is the best. He used to teach in Bombay Scottish, a very, very well-known school in Mumbai, and now he is with us. I am sure you all must have seen him before also. And today's session, we are doing it completely free. You can come over here, learn the entire topic, give your feedback, ask your doubts most importantly. So all of you all can join right now. We are sending the link to you everywhere. Samir sir, can you also post the link on Roughbook family as well?
Yes, sir.
Yeah, so we are posting the link everywhere, guys. You can join with us right now, and it's a completely free session. So today's session, we want you to understand, we want you to evaluate us, and we want you to tell us how we can grow better and connect with you. Not only that, if you want to join the subsequent session of physics, you can go onto the Roughbook app. Obviously, you'll have to download it from the Play Store. Download the Roughbook app. Look out for physics crash course and join it. It is for 2,900, I guess, where you get the entire course. The entire SEM 1 is being taught again. Not only that, you're getting MCQ papers, which you can attempt from your side. And not only that, the discussion of the paper as well. So he's going to give you MCQ papers on each topic. Plus, we are giving you the MCQ of full 40 marks paper. So that is for physics. You can definitely join that right now, right away, today for free. But after this, obviously, you need to pay something for that. That's the subscription cost. We are running five more crash courses. Mathematics, obviously, taken by me. Then we've got English by George Hilbert sir from St. Mary's. Then we've got computers, which was yesterday again free. I'm sure many of you had joined for that by Dr. Prakash Pitroda, again from St. Mary's. Then we've got with us Mr. Paul Machado, the ex-camping principal, who's taking up topo maps from geography as a crash course. And we've got one more crash course, chemistry, by Miss Amna. She's also taking up, very veteran teacher. All the teachers with us are all known, reputed. So we are trying to connect with our motto. So the motto is very simple: reach the remotest child with the best teacher at the affordable price, which is what I am trying to do, so that all of you all can get the benefit at the lowest cost and the best teachers as well. So any course you want to subscribe, go on to the Roughbook channel, subscribe right away, and I'm sure your each penny will be worth, and you will be dealt with all your doubts for sure. Anyone over here who wants to give us some feedback on physics, the sessions that you attended before, so that the crowd knows and they can trust what we are saying? Daisy or anybody, Vaishnavi, anyone would like to unmute and please tell us our feedback? It will be an honor for us, please. Anybody, Daisy, Vaishnavi, Shefali. Come on, Shefali, can I hear it from you?
Can I, sir?
Yes, please, Daisy, go ahead.
So all the crash courses are very perfect. So each and every explanation is understandable, and computer is really amazing. Geography too. So like each and every line, which, as you say, sir, each and every penny where you spend is valuable, sir.
Great.
I wish everyone takes the crash course, sir.
And what crash courses have you subscribed for?
So geography, computers, then maths, physics, chemistry.
Oh, almost all of them.
Sir.
Thank you so much, Daisy, for trusting us and also telling us how we are. It really means a lot. But you never said that I was good.
So you're always good, sir.
Just joking, just joking. So sorry. Anybody else would like to give us some feedback? So Shifali, Vaishnavi, Kenaz, anybody. I want at least 2-3 people to loudly tell everybody how we are so that they can trust us and it will become their benefit eventually more than ours because we are reaching out to them with the best teachers. Anybody out over there? Come on, be bold enough and give us 2 lines. It will mean a lot to us. Shifali, go ahead. Vaishnavi, would you like? Yes, Shifali, go ahead.
Yes, sir. The courses are excellent. And what we really needed at this time was something that adapts to the MCQ based pattern that we have right now. And that's what we get here. So thank you, sir.
Where are you from, Shifali? You said I forgot. Every time I forget, I'm aging.
Sir, I'm from Pune.
Pune. Vaishnavi, can I hear it from you? The last one. I'm not going to take long over here. Yes, Vaishnavi, go ahead.
Sir, the crash courses are really nice and the MCQs are designed in such a way that we do not make any silly mistakes, and then there are so many tricks and tips in every session that we actually need to concentrate on to excel in our board exams.
That's really good insights, Vaishnavi. Good observation. Thank you so much. May I know where are you from?
Sir, Hyderabad, Telangana.
Okay, so boys and girls all out over there on the YouTube channel, I just want to make one thing very loud and clear. The motto is get the best teacher and reach the remotest child, which is what we're doing. Lots of courses are there. There are more than 350 courses on Roughbook app and at a very takeaway price. Come on there, subscribe for whichever course suits you and study. We want to spread the love for studies, and which is what I'm doing. Because of doing this, if you call me a businessman or whatever you want to call, yes, I am. As far as children are getting benefit, as far as all of us are getting benefit, I am trying to create a win-win situation for everybody, and I am proud of my entire team for this. Okay, so guys, if you also want to take the benefit, go to the Roughbook app, subscribe right now, or else at least take today's free session, enjoy it. I'm sure Santosh Nimkar sir is going to give his best. Not only that, you are going to take away something at the end of the session. I can guarantee all of you all about that. The links are being circulated everywhere. Anyone wants to become a part of it, please do so right now. It's free for today. Henceforth, obviously, you'll have to subscribe. Santosh Nimkar sir, a word of wisdom from your side. How do you find the crowd coming in from different parts of the country?
Absolutely fabulous, because actually for the first the interaction was less, but last the class was actually really good. They were interacting, and in the process the interaction is very important, and that is what is happening, and which I am much excited about.
So for me, trust me, I have never taught kids across the Mumbai geographic boundaries. First time I'm doing it and I'm very excited. It really gives me a lot of kick. May I know your views on that, teaching pan India across?
Yes, absolutely, because even I, of course, I mean, hello, yes.
Sir, your voice is low.
No, your voice is very clear, sir. Bacha, something is wrong on your end. I can hear him very clearly. Sir, go ahead, sir.
Yeah. So in fact, I have taught in the villages, rural areas, but I have not taught across the border. So this is a great experience that not even if I have taught in the villages, I have taught in the villages of Maharashtra, but
Okay.
beyond that, I have not taught, and this has given me a great opportunity. Thank you, Mitesh sir.
No, sir. In fact, we are thankful that you are a part of it. It's a privilege for us. Trust me, every day I tell myself that we are really proud of the team. And you are one of the gems. Okay, so boys and girls, without further ado, I am not going to further confuse you all with all these things. Just enjoy the session, and all over to you, Santosh sir. Thank you so much.
Thank you so much.
Hi, sir.
Hi, Akshita, that was you. And please, Mohammed, I think you had some problem with the connectivity. Is that sorted out? Can you?
Yes.
Yeah, okay. Yeah, now today's chapter which we are going to do is light, that is plane surface refraction, and that carries a lot of weight. Now, if you see the entire previously 80-mark paper, the light chapter, entire light, that means including the plane surface refraction as well as curved surface refraction and the scattering portion, the light always used to be at least to 30 marks. So I'm sure in this also the of light, according to my calculation, should be around about 15 to 16 marks. Not only this chapter, including the lenses also. Now, let us start now while teaching topic, if you feel at certain place you need more,
So excuse me.
yes, sure. Yes, Pranjal.
Sir, before starting the topic, I want to ask a question. Like in
Yes.
the between the topic, I cannot ask. So,
Absolutely.
sir, it's from sound. Can I ask, sir?
Sound.
Just one question. Just one question.
Okay.
So it's a very interesting questions. I have very different views of the different teachers. So may I ask your point of view on that?
See, listen, Pranjal, the problem is what, we have a limited time. Last time also the lecture went on till 2.5 hours. If the question takes less time to explain, I will spend that time. Otherwise, I will have to go ahead. You can connect to me definitely later on. I will definitely entertain you. Yes.
Okay, sir. So may I tell the question?
Yes, sure. Please go ahead.
Sir,
quickly.
the question is, sound wave is a wave that is produced due to. The first option is vibration of particles. Second is disturbance of particles.
Akshita, one second. Akshita, could you please mute your mic? Okay. Yes, Pranjal.
So the first option is vibration of particles. Second option is disturbance of particles. Third option is turbulence of particles. And fourth option is all of the above.
All of the
above.
All of the above, of course.
But sir, the vibration is a to and fro motion and then coming back to the mean position. Disturbance can also be from one place to another.
Pranjal, this will take a little more time to explain because this is leading to the discussion. I cannot spare time at this stage.
Okay, sir. Okay.
Because that will lead to how the amplitude and everything. At this stage, I cannot spare that much time.
Okay, sir. No problem.
Thank you. Yes, Gauri, you are asking something. Okay, let me start with. Okay. Now refraction. Yeah. Now refraction is light when it enters from one optical medium to another. Now, if you see this pattern, now in this pattern, the beaker filled with water is being moved in front of the checkboard and the patterns are changing. Now, the reason being when light passes through it, it suffers refraction. And since the surface is curved, so the refraction varies and therefore you see the pattern. So the refraction is the bending of light when it enters from one optical medium to another, and the cause of refraction is the change in the speed of light. Okay. Now, when light enters from one medium to another medium, due to change in the speed, it bends. Now, when light enters from rarer to denser medium, it bends towards the normal and there is decrease in the speed of light. And conversely, when it enters from denser to rarer medium, it bends away from the normal and there is increase in the speed of light. Now, related to the light, you should know certain terms. I think wherever there is important, I'll spend more time. The definitions are all which are not asked through the examination point of view. I will quickly go ahead, but still, if you feel there is any doubt or any problem, you can always ask. Okay. Now, optical medium is any medium which allows the light to pass through it. Opaque medium means which does not allow the light to pass through it. Denser medium. Now, very often the students have concept in their mind. Denser means mass upon volume ratio, density is greater. Now, here when we are talking about denser medium, means the medium in which the speed of light decreases. It is not related to the mass upon volume ratio. Rarer medium, it is the medium in which the speed of light increases. Okay. Now, when light enters from denser to the rarer medium, it bends normal. When it enters from rarer to denser medium, it bends towards the normal. Now, when light enters from denser to rarer medium, since it bends away, angle of incidence is less than angle of refraction. And when the light enters from rarer, because the questioning can be based on this, okay, when the light enters, if the angle of incidence is greater than the angle of refraction, okay, whether the light is traveling from denser to rarer or rarer to denser. So the questioning can be done based on this. So you should know. When light enters from rarer to denser medium, it bends towards the normal. So since it bends towards the normal, angle of refraction is less than angle of incidence. Now, with respect to the refraction, you should know these terms. Now, whenever any lights, yes, Daksh.
Hello, sir.
Yes, Daksh.
Sir, I don't get the concept of when speed of light decreases, how its direction changes, sir. I mean, the speed of light is going one medium, its speed obviously decreases, but how its direction changes?
See, the thing is that, in fact, if you imagine the chain of particles, okay, now light ray when enters into the other medium, now imagine this is the wavefront of light. Now when it starts entering, okay, can you see the border enters from one medium to another medium?
Yes, sir. Yes.
Yeah, okay, so their speed decreases, but the remaining portion speed is different.
Okay.
Have you seen when you are marching on the ground, when you are taking the turn at the corner, the inner line has to move slowly, but the outer line has to move faster in order to be in the same line. Yes. So in order to be in the same line. So the very fact that the speed changes over here. So in case of light can also be considered as a particular nature. So when these particle enters inside, but these are in different mediums, so there is difference in the speed. So accordingly, there is change in the direction. But I'm sure this question will not be asked to the examination point of view. This is your personal understanding. It's okay. We cannot spend more time than this. But you can, if you can think on this line, students are marching and on a circular track. What do you think, the inner line as well as outer line will march with the same speed?
Sir, can you explain also?
Pardon? The inner line as well as outer line, will they march with the same speed?
No, sir.
No. Correct. So if the file is marching, this is 1, this is 2, and this is 3. So the inner students travel less distance. Comparatively, the outer students travel more distance. So they have to keep the pace. And here they travel maximum distance. So because of this, because of this, when the light enters medium to another medium, the wave from this port, they have already entered into the other medium, but not the other portion. So when they start with the different speeds, so they enter inside over here. Actually, one second, I had that diagram which I had shown. Can you see this?
Yes, sir.
Are you understanding? Now here the speed is different. Here enter the medium, the speed is different.
Yes, sir. Understood, sir.
Yeah. Okay. But I would suggest that let us spend more time on the questions which are related to the examination point of view. This is better, but I'm 101% sure there won't be any question based on this. Okay. Okay. Now with respect to light, whenever any light strikes a surface, always a part of the light energy is reflected. So that's a partially reflected ray, and part of the light energy is refracted. Now here the light is entering from rarer to denser, so it bends towards the normal. So the angle made by the incident ray with the normal is the angle of incidence. Angle made by the refracted ray, the ray which enters into the other medium, is the refracted ray. So the angle made by that ray with the normal is the angle of refraction, and this is the angle of deviation. Okay, so the refracted ray or light which is refracted will always have less intensity compared to the light which is incident, because whenever the light strikes the surface, three things happen. Part of the light energy is absorbed, part of it is reflected, and remaining is refracted. Now, how much is absorbed, how much is reflected depends upon the given medium is how good refracting medium or how good absorbing medium or how good reflecting medium. Okay, that's what I've explained just now. Now, laws of refraction. Now, similar to the laws of reflection, the incident ray, the refracted ray, and normal at point of incidence lie on the same plane. Okay. Then, second law of refraction, the ratio between the sine of angle of incidence. Now, and sine of angle of refraction is constant for the given pair of media and for given wavelength of light. Now, what do you mean by this? Now, first of all, you should know when I talk about sine corresponds to the angle in a right angle triangle. So sine of this angle will be opposite upon hypotenuse. Now, if the size of the triangle increases, but the angles remain the same, still the ratio between this and this will remain the same. So size does not matter. So whenever the light strikes a surface, okay, and light enters, this is a normal.
Sir, I didn't get this.
No, I haven't. What, this size? Which part?
Yes, sir.
Yeah. No, what I'm trying to say is that sine ratio is opposite upon hypotenuse, correct?
Yes, sir.
So even if I take a bigger triangle, but suppose this angle is 35. So whatever is the ratio between this and this will be same as if this is a bigger triangle, then the ratio between this and this will be the same. Suppose this is 2 and 5, and suppose this is 4, this will be 10. So the ratio will remain the same. Concept of similarity.
Okay. Thank you, sir.
Yeah. Now, when the light enters, say this is a rarer medium and this is a denser medium. So denser to rarer medium, it bends away from the normal. So in this case, this is the angle of incidence. So when I say the ratio between sine of angle of incidence, which means that I need to have this angle in a right angle triangle. So if I drop a perpendicular here, or if I drop a perpendicular over here, or if I drop a perpendicular over here, does not matter, because this length upon this length will give you sine. Even if I drop it over here, this length upon this length will give you sine. This length upon will give you sine. And angle of refraction is this. So complete right angle triangle anywhere. Maybe here, maybe here. So sine R will be this length upon this length. Sine R, if you consider this triangle, then this length upon this length will be the same. That's why size of the triangle does not matter. Okay. So the Snell's law states that the ratio between sine of incidence, That means if this ray has different angle, then correspondingly angle of refraction will change in such a way that sine I upon sine r will remain the same. Is that clear?
Yes, sir.
Yes, sir.
Yeah, 1 second. Okay. Now, now what do you mean by refractive index? Now, refractive index is the constant ratio between sine of angle of incidence. Now, one more thing I forgot to tell you about this. The ratio between sine of angle of incidence to the sine of angle of refraction is called as refractive index, and which is denoted by mu. So if the refractive index is high, that means the ability of that medium to bend the light is greater. If the refractive index is less, then the ability of that medium to bend the light is. So higher the refractive index, more is the ability of that medium to bend the light. Lower refractive index means lower is the ability of that medium to bend the light. Okay. So the ratio between, so the two laws of refraction, the incident ray, the refracted ray, and normal lie on the same plane. And the ratio between sine of angle of incidence to the sine of angle of refraction is constant for a given pair of media. Because suppose the light is traveling, say from glass and to air. Okay. The light is traveling from glass to air. So if I have angle of incidence equal to 30, okay, and say angle of refraction is equal to 40, arbitrarily I'm choosing the values, okay, then if I have angle of incidence 30 but other medium is different, then the ratio will not remain the same. The ratio will remain constant for the given pair of media. And for given wavelength of light, that means in place of this, if there is red light, if there is violet light, if there is green light, then correspondingly the angle of refraction will be different and the ratio will differ. But for, if suppose this is a green light, and if I keep on changing the angle of incidence of green light, correspondingly the angle of refraction will also change. Then the ratio of sine I upon sine r will remain constant for green light, but that will not be same as for violet light. So in other words, the ratio,
Sir, can you explain once more?
when the light enters, suppose this is air and this is glass. Okay. Now I have light to be incident over here. Okay. And let us say you find red light,
Red color.
and suppose if I take say blue light over here, traveling from air to glass. Then if I find out the angle of incidence may be same, say 30. But here the angle of refraction will be different. Here the angle of refraction will be different.
Yes.
Angle of refraction will be more. Here the angle of refraction will be less. But if I keep on changing the angle of incidence for same color, correspondingly the angle of refraction will change, but sine I upon sine r will remain the same for that color. Got it?
Yes.
Sir, which will bend more, red or violet?
Blue will bend. See, the
Why?
is violet, indigo, blue, green, yellow, orange, red. So red will bend the least and violet will bend the most.
Sir, why, sir?
Pardon?
Why?
It depends upon the wavelength. The shorter the wavelength, the bending is more. And
So then no color.
What is wavelength?
Acha, wavelength is, now if this is a wave, now if I talk about a wave, it will flash this pattern in front of your mind.
Yes, sir.
Yes, sir.
So from here to here, it corresponds to one wave. One projection and one depression corresponds to
Yes.
that is called as wavelength. Okay.
Sir, what
Yes,
is
sir.
The smaller the wavelength,
Different wavelengths have different colors, sir.
pardon?
The difference in the wavelengths cause different colors, sir.
Yes. Yes. Okay.
So like violet will have the most wavelength, right?
I didn't get it. What did you, Violet? What did you say?
I know, like violet will have the least wavelength, right?
Yes, shortest wavelength. Yeah.
So why is it that if the wavelength is short, the like it'll bend more? Why is it like that?
Sir,
See, the
why
thing is that
color?
one second.
Color?
Now, 1 second. See, my aim for this lecture is to prepare them for 10 standard. Now, what happens, like with this question, the session can go for 3 to 4 hours also. So I would appreciate if you ask the question related to the exam. See, this is not general teaching. The purpose of this lecture is to prepare you for the ICSE exam. And the questions which I'm getting is not pertinent to that. So if I spend my time later on, it will be a problem. So if I would appreciate if at the end you wait, like once I finish, then I can administer your doubts.
Okay, sir.
Yeah, thank you. So violet wavelength, see, remember for any wave, you have learned the basics of this. V is equal to F lambda. So in air and vacuum, all the colors travel with the same speed. So those who have smaller frequency wavelength, they have higher frequency, and those who have smaller frequency will have higher wavelength, but ultimately the product of the two always remains the same. But this is true for vacuum and air. When they enter into any other medium, the moment they enter into any other medium, the violet has the least speed and red will have the maximum speed. Okay, the speed. Now, why the speed changes at this stage, it is beyond the scope of discussion. Because with respect to the knowledge which the 10 standard level, I cannot explain. So you'll have to go beyond the board for that. Okay, you'll have to go to the properties of electromagnetic radiations for that. Okay.
Hey, nobody. Hey, nobody.
Sir, I have a doubt.
Hey, kya hai?
Who's speaking?
Hey, kate.
Hello, can any who's speaking this mic?
मैं बोल रहा हूँ बे.
Sir,
Sir, I think so.
Krishnan Gala.
Who's that?
Krishnan Gala.
Yeah, Krishnan, yes.
I think he speak.
Okay.
Sir, I have a doubt.
Yeah, see.
Sir, how is the dependence of angle of deviation is on color?
Sorry, Anjali. Sorry to interrupt, sir. Sorry for the disturbances, sir. Like there might be some unwanted people who might be joining. We won't have any control on this, but I'll try to be very specific. Like if any of these things happens again, I'll straight away remove those participants. And I am being very specific. We are keeping this session for your learning, and so that everyone should get benefit out of this. The teacher teaching who is the teacher who is teaching over here is almost a stalwart. Okay, and like these all teachers are stellar, so please respect, and if you want to study, then and only then join the session. Otherwise I'll be like forced to remove you all from the, like, whoever is creating this nuisance. Sorry for the interruption, sir. You may continue. Sorry, Anjali, you could ask your doubt and go ahead now.
Thank you so much.
Yeah.
Sir, actually my doubt was that what is the effect of wavelength on light and relationship between wavelength and the two mediums?
See, the wavelength when it enters from one medium to another medium, actually all these problems, if you pay attention, will be taken care of. But the problem is that when I'm starting and you want to solve your doubts, actually the doubts would be appreciated when anyway, but now you have asked, I'm telling you. Now, when it enters from rarer to denser medium, now V is equal to F lambda. Correct? Now, when light enters from rarer medium to denser medium, the speed decreases. Now, you know that for a given frequency can never change. Frequency of depends upon the source. That never changes even if it enters from one medium to another medium. So obviously the velocity is increasing due to increase in the wavelength, and if the velocity decreases due to decrease in the wavelength. So obviously when the light enters from rarer to denser medium, the speed decreases, that means the wavelength decreases. When it enters from denser to rarer medium, the speed increases, so the wavelength also increases. Or rather, wavelength increases, the speed increases. Is that clear?
Yes, sir.
Angle of deviation. The shorter the wavelength, the more it bends.
So what is angle?
Pardon?
What is angle of deviation?
Yeah, angle of deviation. I just now showed it to you here. This is the angle. Now this is the direction of the incident ray. But due to refraction, it bends. So the angle through which it bends is the angle of deviation.
Okay, sir.
Is that clear?
Thank you, sir.
Yeah. Okay. Now refractive index is the ratio between the sine of angle of incidence to the sine of angle of refraction. So it is denoted by A mu B, or mu, it is denoted by mu, but we also specify the media. When I say A mu B, that means the light is traveling from medium A to medium B. Angle of incidence is in medium A, angle of refraction is in medium B. And sine I upon sine R. Now, I is the angle of incidence, R is the angle of refraction, and A mu B is the refractive index of medium B.
Some mu.
Mu is the alphabet, Greek alphabet. Mu is a Greek alphabet. Excuse me. Hello. माझा लेक्चर चालू आहे बाबा. ऑफकोर्स ऑनलाइन नेशन वाइज लेक्चर चालू आहे. लेक्चर चालू आहे माझं. Okay. Now, it is observed that when you take the ratio between the lecture is going on here. What is going on? Sorry. So, when I say A mu B, it may, and it is a sine I upon sine R.
Sine R.
Okay. Now this ratio is also found out to be equal to speed of light in medium A upon speed of light in medium B. So I can define refractive index in terms of the speeds of light in the two media. Now, in this case, there is a need for finding out the absolute refractive index. Let us say if I talk about the refractive index of glass. Now, there is a finite possibility that some person may be talking about refractive index of glass with respect to water. Other person may be talking about refractive index of glass with respect to, say, alcohol. So in that case, the ratio will be different. So to have the proper understanding, whenever we do not specify the other medium, when I mention that it is a refractive index of glass, it is international convention that the other medium is to be vacuum or air. Other medium to be assumed to be vacuum or air, and such a refractive index is called as absolute refractive index. Such a refractive index is called as absolute refractive index.
Sir, why it is only taken in the ratio of sine, not any other trigonometrical ratio?
No, actually what happened, initially when Newton was studying it, Newton found out that the ratio between I upon R was constant. Okay. Now, after that, Wilbrod Snell found out. Now, I upon R ratio was constant when the angle was very small. Angle of incidence was very small. But as the angle of incidence increased, the I upon R ratio was not constant. later on, Wilbrod Snell found out that the ratio remains constant for, the ratio remains constant for sine of angle of incidence. The ratio is constant for given pair of media for sine ratios. You can see if sine I, you have learned trigonometry. If I'm talking about sine I, correspondingly cos 30 will also be constant. It may not be same as out of this, but you have to define with respect to, see, your parents decide to give you some name. Now, why they have given you this name? So the thing is that whatever the Wilbrod Snell found out, that the ratio between sine of angle of incidence and sine of angle of refraction, he could have defined with respect to the other trigonometrical ratios also, and the ratio would remain constant.
Sir,
International, there has to be convention where one cannot define in terms of sine, someone other person decide in terms of cos. So then there is a problem in understanding or communication. That's why it is in terms of sine. Yes.
so when we are saying that the refractive index of one medium with respect to the other, so like for example, refractive index of medium A with respect to B. So will it be different when we're saying B with respect to A, or will it be the same?
It will be reciprocal. Now see, if suppose speed of light in medium A is, let us say, x, and speed of light in medium B is y. So when I say B mu A, it will be B upon speed in y, speed in A. What is speed in y? B, y. So it will be reciprocal.
Okay. Yeah. Thank you, sir. And the first medium written is from where the light is incident, right?
Yes.
Okay. So, sir, over there in the example that you gave, so it's incident from vacuum and it goes into gas, into
glass.
into glass.
Glass, yeah.
Okay.
So when I don't mention any other medium, it is assumed that it is with respect to vacuum or air.
So, sir, when we're essentially talking about the refractive index, then it's usually of the second medium, right?
Yeah.
It really depends.
That's
on
what
the
I said.
second
It is a
medium.
refractive index of B with respect to A.
Okay. Yeah. Thank you, sir.
Yeah. So I can also write down the refractive index in terms of speed. So 1 mu 2 means speed in medium 1. Whichever is the first medium will be in the numerator, second medium in the denominator. So refractive index of 2 with respect to 1. If I write down A and B over here in the numerator, speed of light in medium A upon speed of light in medium B. So it is a refractive index of B with respect to A. So I hope this convention is clear to you.
Yes, sir.
Okay.
Yes, sir.
Now, as the frequency of the wave remains constant in any medium, therefore it can also be defined as the ratio between the wavelengths. Now let us say when I take A mu G. So it is speed of light in medium A upon speed of light in medium G. But we have also learned that V is equal to F lambda. So the speed in air will be frequency into wavelength of light in air upon frequency into wavelength of light in glass. But you know that frequency of light when it enters from frequency of light when it enters from one medium to another medium, the frequency doesn't change, right? This is a property of the wave which you have learned last year. When a wave enters from one medium to another medium, its frequency remains same, but the wavelength changes. I explained it before also. As the is equal to F lambda, as the wavelength increases, the speed increases. Wavelength decreases, but the frequency doesn't change. So the light is entering from air to glass. So obviously its frequency doesn't change. So when I'm taking the ratio between the speeds, it is as good as taking the ratio between the wavelengths. Are you understanding?
Okay, sir.
Yeah.
Yes.
So as frequency of wave remains constant.
Hello, sir.
Yes.
Mother
as the frequency of wave remains constant in any medium, therefore it can also be defined as the ratio of wavelength of light in medium 1 to the wavelength of light in medium 2. So you can define it as a ratio between. So instead of speeds, I can also write down wavelength in 1 upon wavelength in 2. Okay. So 1 mu2 is lambda 1 upon lambda 2. Is that clear?
Yes, sir.
Okay.
Yes.
Yeah.
Yes, sir.
Yeah. Now, what are the factors on which the refractive index of medium depends? So it depends upon the temperature. As the temperature changes, the refractive index also changes. With the increase in the temperature, the refractive index decreases. And with the decrease in...
Sir,
Yes.
Sir, in question diagram should come.
In question what?
MCQ diagram should come. MCQ. Diagram should come.
I'm not understanding. MCQ diagram what?
Sir is asking whether diagram questions will be there in MCQ.
Yes, it can be asked. Yeah. It is inversely proportional to the wavelength of light. So wavelength of light is smaller, the refractive index will be higher. That is why violet bends the most. Its wavelength is less. So the refractive index is higher. Or refractive index is higher. That's why the shorter wavelength bends the most. So wavelength bends the most: violet, indigo, blue, green, yellow, orange, red. So violet will have maximum wavelength and red will have the least wavelength. Okay. And it is inversely proportional to the speed of light in the medium, because you need to keep it in mind, this relation. Mu is equal to say A mu G. So speed of light in medium A upon speed of light in medium G. Okay. Now the speed of violet light. Yes. Speed of violet light is maximum. Minimum. And speed of red light, violet, indigo, blue, green, yellow, orange, red. So speed of violet light is minimum because V is equal to F lambda. So the velocity is minimum for violet and maximum for red. So the speed of light in air is always constant. So 3 into 10, 8. Okay. But speed of light in glass is minimum for violet. So if the denominator is smaller, the fraction. And if the denominator is greater, then the fraction is smaller. That's why the refractive index is minimum for red and maximum for violet. Okay?
Yes, sir.
Yeah.
Yes, sir.
Yeah. Now it depends upon the nature of the medium also. Basically, the third point is the same as refractive index only. So as the nature changes, the refractive index. The first 2 points are important. Yes.
Third point.
What?
Nature. Third point can you explain?
Daisy, what is he saying?
Sir is asking to explain the third point.
It depends upon the nature of the medium. That means for glass, the refractive index is different. For water, the refractive index is different. Okay, so as the nature of the medium changes, the refractive index changes. Clear, Mohammed?
Yeah.
Okay. Now, this is one more important point. Now, optical density is different from density. Now, I have told you this before, that it is not the ratio of mass upon volume. You may find some example where the density of the medium is less, but its optical density is greater. Now, for example, alcohol. Now, the density of alcohol is nearly 0.8, but the density of water is 1 gram per cubic centimeter. So, alcohol is less dense than water, but optically, alcohol is more dense than water. The ray will bend more in alcohol than in water. So, the refractive index of light, refractive index of alcohol is more compared to the refractive index of water. Whenever we are talking about density, we are referring it to the optical density and not mass upon volume ratio. Is that clear?
So what's the proper definition of optical density?
Optical density, it's like this. How do you measure mass in terms of, or inertia in terms of mass? Inertia is a tendency of a body to be in its state. So you measure that tendency in terms of mass. So similarly, the optical density is measured in terms of refractive index. Are you understanding?
So, sir, optical density is only for light, and
yes,
the
it is
normal
only for
density
light.
is simply for, yeah. So over here we're talking only about this density, right? Optical
Yes,
density.
optical density. The bending ability of the medium. So if I'm talking about optical density, you can define the ratio of that means you can give the definition of refractive index. What you need to keep it in mind, optically more denser means the ray will bend towards the normal, the speed will decrease, like the speed of light. Optically less dense means speed of light will be more. But the optical density is measured in terms of refractive index. Okay.
Thank you, sir. So do we have to know the different optical densities of different mediums?
No. I see, as a procedure, you need to know the refractive index only of air, diamond, and water. That's all.
Okay, thank you, sir.
Yeah.
Sorry for the interruption, sir.
Yeah.
Sir, don't admit anyone from now onwards. Okay,
Okay.
sir. I'll admit from my end. Okay, sir. Don't admit anyone.
Thank you. Thank you. Absolute refractive index. It is the ratio of speed of light in vacuum to the speed of light in medium. I have already spoken about this. Okay, whenever we talk about the refractive index in terms of the when the other medium is vacuum. So ratio between the speed of light in vacuum. Now for your level, speed of light in vacuum and air is the same. Okay, the speed of to the speed of light in the medium, or it could be the ratio between wavelength of light in vacuum upon wavelength of light in medium. Now, as the speed of light in vacuum, the absolute refractive index is always greater than 1. Because see, the maximum speed is in vacuum. Whenever I'm talking about the refractive index, obviously it is of any medium other than vacuum. Do you agree? So that
Yes, sir.
denominator will always be smaller than numerator. Because
Yes, once
in
again.
any other medium, the speed of light decreases.
Yes, sir.
Denominator is always less than the numerator. So can the absolute refractive index be less than 1?
No, sir.
It can never be. That's what I've written it over here. As the speed of light is maximum in vacuum, the absolute refractive index is always greater than 1 because my numerator will always be greater than denominator. So if the numerator is greater than denominator, the refraction will always be greater than 1. Okay. Now, what are the conditions under which no refraction takes place? When the refractive indices of the two media are the same, then the light travels undeviated from one medium to another medium for any angle of incidence. Okay. Now, please understand, there may be different media, their chemical composition may be different, but their ability to bend the light may be same. Their ability to bend the light may be same. So in that case, the light will travel from one medium to another medium without bending for any angle of incidence. There won't be change in the speed of light also. There won't be change in the speed of light. Is this clear? Is this point clear?
Yes,
Yes, sir.
Yes, sir.
And there is... Yes, Mohammed?
Yes.
Yeah. Now, in fact, this video, I mean, I cannot afford to show the video at this stage because it will take time. We won't be able to finish. Okay. Another case is when the light ray strikes the surface of the medium normally. That means even if the refractive indices of the two media is different. So when the refractive index of medium 1 is greater than 2 or 1 is less than 2. In both the cases, if the light ray enters from one medium to another medium striking normally, then it will travel undeviated. But if it is striking at an angle, then there will be refraction. So when the refractive indices are different of the two media, No refraction will take place only if the rays strike the surface normally. But in this case, there will be corresponding.
Hello, sir. Hello, sir.
Yes.
Sir, you explain. I will understand.
Yeah. But in this case, there is corresponding.
Hello, sir.
Yes.
No, sir. Explain.
Corresponding change in the speed of light. Okay. Now, when it is entering from rarer to denser, the speed will decrease. Denser to rarer, the speed will increase. Okay. But when the refractive indices are same, the speed will also not change and the bending will also not happen. And that in that case, it will happen for all angle of incidences. There won't be bending, there won't be change in speed. So no refraction takes place under two conditions. When the refractive indices of the media is same, then for any angle of incidence, no bending takes place and no change in the speed. And if the refractive index of the media is different, the bending will take place if the angle of incidence is, if the ray is not incident normally. But if it is incident normally, there is no bending, but there is change in the speed of light. Is that clear?
Yes, sir.
Yes, sir.
Yeah.
Yes.
Now, now what is the principle of reversibility of light? Now, the principle of reversibility of light states that under any phenomenon of light, whether it is a phenomenon of reflection, refraction, diffraction, scattering, whatever phenomenon of light, whatever path the light takes, if you reverse its direction, it will follow the same path. So if it enters from 2 to medium 1, it travels this path. If it travels from this medium, from medium 1 to medium 2, if I reverse the direction, it will follow the same path. That means angle of incidence, refraction. If angle of refraction becomes angle of incidence, then angle of incidence will become angle of refraction.
Reverse.
Even if it is reflection, it is applicable. So if the ray goes along this path, after reflection, it goes over here. So if it is incident along this path, after reflection, it goes along this path. Learn that in reflection also.
Yes.
Yeah. Now, relation between A mu B and B mu C. Now, actually, I had explained this, but through the examination point of view, this is not very important. So if it is not clear, don't bother to understand. I'll just explain and I'll go ahead. Because while explaining, I had already explained it to you before also. A mu B is speed in A upon speed in B. B mu A is speed in B upon speed in A. So if I multiply, I'll get speed in A upon speed in B because A mu. And this will be speed in B upon speed in A. So this gets cancelled and this gets cancelled. Get 1. So A mu B and B mu A, the product is 1, which means that they are reciprocal of each other. So A mu B is equal to 1 upon B mu A. Now,
this we have to by heart. This we have to by heart.
Yeah, this you need to know. A mu B is equal to 1 upon B mu A. Now here, if the light is entering from medium A to medium B to medium C, then A mu B will be speed in medium A upon speed in medium B. But if the same entering from B to C, then B mu C will be speed in medium B upon speed in medium C. Then what is the refractive index of medium C with respect to medium A? That will be A mu C, and according to definition, it is speed in A upon speed in C. But you should know that this is equal to the product of these two. Because if I take A mu B, it will be speed in A upon speed in B. If I take B, it is speed in B upon speed in C. So this gets cancelled. What is left? Speed in A upon speed in C, which is A mu C. Correct?
Yes, sir.
Yes, sir.
A mu B into, but this expression is not important from the examination point of view. This is important. Okay?
Yes, sir.
Yeah. Now the refraction through a rectangular glass block. Now when light enters, okay, on the surface, now refraction through a rectangular. When you understand this, you should be able to apply this knowledge in every situation where the opposite surfaces are parallel. It's not that, okay, this is how the refraction will take place only through a rectangular glass block. Suppose this portion is broken here, this portion is broken over here, still the refraction would remain the same so long as the opposite surfaces are parallel. Even if my refracting medium is like this, and it is broken, but the refraction through these two surfaces will be same as whatever is the refraction through a rectangular glass block. Now the rays strike the surface. This is the dotted line indicates the ray direction along which it would have traveled. It is entering into a denser medium, so it bends towards the normal. This is the angle of incidence. This is the angle of refraction. When it strikes the other surface, again there is a refraction from denser to a rarer medium, and the ray bends away from the normal. And since opposite surfaces are parallel, the incident ray direction, emergent ray direction, they are parallel. Okay. Now you can do this also. Now, if you take, so these are the labeling: incident ray, the refracted ray, the emergent ray, and the perpendicular distance between the direction of the incident ray and the emergent ray is called as lateral displacement. That means when the ray enters and due to refraction, when it emerges out parallel, by whatever amount it laterally gets displaced is the lateral displacement. Okay, it is a perpendicular distance between these two, and you know that the distance between the parallel lines anywhere you measure will be the same. Now, since opposite surfaces are parallel, angle of incidence will always be equal to the angle of emergence. This angle will always be equal to this because opposite surfaces are parallel. So normals drawn to them will also be parallel. So whatever is this angle will be same as this angle by alternate angle property.
Yes, sir.
So if this is angle I and this is angle R, if the light enters from glass to air, if the angle of refraction becomes angle of incidence, angle of incidence will become angle of refraction. So the angle of refraction becomes angle of incidence at this point. Suppose I take this angle as say 40 degrees and say this angle as 30 degrees. So obviously when the light enters from glass to air, if the angle of incidence is 30, angle of refraction will be 40.
Yes, sir.
So the angle of incidence is 30 at this point. So the angle of refraction will be 40. So angle of incidence is same as angle of emergence.
Refraction.
Yeah. No, not refraction. Angle of incidence is same as angle of emergence. These angles are equal. Corresponding angle of deviations will also be equal.
Sir, R1 and R2 are the angles of refraction, right?
No. R1 is the angle of refraction at the first surface. And R2 is the angle of incidence for the second refraction. I am denoting them by R1 because both of them are same. There are two refractions, one at this surface and one at this surface. Clear?
Yes, sir.
Can you explain once more?
See here what happens. If the angle of incidence is 40 and arbitrarily let us say angle of refraction is 30. Now according to the principle of reversibility, if the light enters from glass to air, if this is 30, this will be 40.
Yes, sir.
Okay. So by alternate angle property, since opposite surfaces are parallel, the normals are also parallel. So this angle same as this angle. So this angle is also 30. So if the angle of incidence is 30, angle of refraction will be same as that of this 40. Is that clear?
Sir.
Yeah. Okay. Now, I have already explained you what is lateral displacement. Now, factors affecting the lateral displacement. Now, lateral displacement is directly proportional to the angle of incidence, because if the angle of incidence increases, the lateral displacement also increases. It is directly proportional to the refractive index, because if the refractive index of the medium is greater, suppose this glass is of greater refractive index, then the same ray would not travel along this path, but it will bend more. I told you that if the refractive index is greater, that means the bending. So obviously when it comes out parallel, what happens to the lateral displacement?
Increases.
Increases.
The refractive index increases, the lateral displacement increases. Then
Yes.
it also depends upon the block. Now, if suppose my block is only this much wider, not this much, but only this much, then what will happen? Ray which has refracted over here, this ray which has refracted over here, and now it will strike the opposite surface at this point. The medium
Yes,
will
sir.
at this point.
Yes, sir.
It will come parallel. So width is less, the lateral displacement is less. The width is more, the lateral displacement is more. Is that clear?
Yes, sir.
Yes.
Okay. And the fourth point is actually same as that of the first point, because inversely proportional to the wavelength of light. That means violet will bend, the lateral displacement will be maximum for violet, because violet bends the most. Out of all the colors, violet, indigo, blue, green, yellow, orange, red. Suppose at the same angle of incidence, all colors are incident. Out of that, violet will bend more. Then lesser than that, then so accordingly, the lateral displacements will change for different colors. So it is maximum for minimum wavelength. So it is maximum for violet and minimum for red. Clear?
Yes, sir.
Yes.
Okay. Now,
Yes.
refraction through a triangular prism. Now, when I talk about the triangular prism, it is a medium bounded by 3 rectangular surfaces. This is one rectangular surface. Okay. This is second. So this is one rectangular surface, second rectangular surface, and the lower one is the third rectangular surface. And it has 2 triangular surfaces. So these triangular surfaces are parallel to each other. Triangular surfaces are parallel to each other. So if the light enters from first triangular surface and comes out from the other triangular surface, the refraction would be same as that of the refraction. Refraction through a rectangular glass block. Refraction through a rectangular glass block. But when it enters from this medium, when it enters from 2 inclined surfaces, Samir, hello Samir. When it enters from these angled surfaces, then the refraction will be different. Okay.
Yes, sir, tell me.
And then this, I don't know whether these are from our group or the outside. They are continuously disturbing.
Sorry, sir.
I don't know. These outsiders are continuously disturbing. I said. Then actually, those who are interested, they are getting disturbed. They are not able to concentrate.
Sir, we won't admit from now onwards. That's the case now. We'll go with this only. Those who are already in, if they misbehave, I'll straightly put them out. I'll remove them. So they won't be able to join.
Okay.
Sure, sir.
Thank you. Now, when we show the refraction,
hello, Hari is out now. Anybody else? Come on, guys. Let's not waste anybody's time. If anyone wants to misbehave now. I'll be putting you out straight away.
Thank you, sir, Samir. Okay. Now, this is the direction of the incident ray. So it will travel undeviated. Now, it is entering Okay. Now the ray is incident normally. So it enters and it is entering from rarer to denser medium. So it bends towards the normal. So normal is here. So this is the refracted ray. Now at this surface, from denser to rarer medium, and it bends away from the normal. So that is the emergent ray. Now the angle made by the incident ray with the normal is the angle of incidence. Angle made by the refracted ray with the normal is the angle of refraction. Angle made by the emergent ray with the normal is the angle of emergence. And if you produce the incident ray incident ray forward and emergent ray backward, the angle between them is the angle of deviation. Angle between the angle of deviation. Now, angle of the prism. The angle between the two inclined surfaces is the angle of the prism. Okay. Now, angle of deviation, already explained it to you. It is the angle between the incident ray and the direction of the emergent ray. Now, we know that this angle D is nothing but the deviation which is produced at the first surface. The ray, this is the direction of the ray. This is the refracted ray. So by this much amount, the ray bends. This for second surface, this is the incident ray, this is the refracted ray. I'm talking about refraction at the second surface. Then this much is the deviation. So this is vertically opposite to this. So addition of these two angles is equal to this angle. So the angle of deviation is nothing but sum of the angle of deviation at the first surface as well as at the second surface. Is that clear?
Yes, sir.
Yes.
Yes, sir.
Yeah.
Sir,
Yeah.
the angle of deviation on the first and second surface, they both are equal, right?
No. They will be equal only in a particular condition during minimum deviation, but not always.
But sir, the prism it's uniform and the light ray is only one. So sir, why not?
This in one particular case it may be, but it cannot be always. That's what I'm trying to. Every time the ray will be parallel to the base. As angle of incidence changes, angle of refraction changes, the ray's inclination will change, na?
Okay, sir.
Sir, but
So over
if
here
it's
there's
monochromatic light, then
Pardon, I didn't get it, Anjali.
sir, but if it is a monochromatic source of light, then
1 second.
So can you explain that also?
so there is only one source of light, right? So
1 second.
sorry, sir.
No problem. Now I allow red light to be incident here. So when angle of incidence is less, angle of refraction is also less. As I increase the angle of incidence, angle of refraction will also increase. As I increase this further, this will also increase. So will it be parallel all time?
no, sir.
No, sir.
No, sir.
Are you understanding what I'm saying now?
Yes, sir.
Yes, sir.
If it is monochromatic, it doesn't matter. But as angle of incidence changes, angle of refraction changes. So you can the angle of deviation same.
Okay.
Yes,
Thank you, sir.
Thank you, sir.
So the thing we have in the book, it only works for that condition, right?
Yeah,
For the rest.
that is for minimum deviation, only for minimum deviation. Because only minimum, see, in refraction through rectangular glass block, I is always equal to E. But in I is not always equal to E.
Okay.
So
Yes,
when
sir.
I is equal to E, that time the deviation through the prism is minimum. And since it is an isosceles prism or equilateral prism, that time the refracted ray will be parallel to the. Okay.
Thank you, sir.
Yes, sir.
And all these derivations have given examination point of view, they are not important. What you need to know is this expression. Sum of angle of incidence and angle of emergence is always equal to R A plus D.
Excuse me, sir.
E is equal to A plus D. Yes.
Sir, is it compulsory to have the angle of prism is equals to 60 degree for angle of minimum deviation case?
No. Minimum deviation is there through every prism. Na? You cannot have only equilateral prism. There are so many prisms. You can have 30, 60, 90 prism. You can have 45, 45, 90 prism.
So, sir, it's not a part of the condition.
No, no.
Okay, sir.
Angle of incidence is equal to the angle of emergence when there is minimum deviation. And the refracted ray will be parallel to the base only if it is an equal isosceles prism. Yes, Mohammed? What you need to know is this expression. I plus E is equal to A plus angle of deviation. That is true. Okay. Now,
So what will be the formula to calculate the minimum angle of deviation?
what will be the formula?
To calculate the minimum angle of deviation.
Yeah, 1 second. Now you know that I plus E is equal to A plus D. So when the angle of minimum deviation is there, that time I and E are equal. So I can replace E by I.
Yes, sir.
So you get dm is equal to 2I because I plus I minus A.
Yes, sir.
Clear?
Sir,
Yeah.
sorry for disturbing again, but the normal for each incident ray is different, right? Like if you change the angle of incidence or the
No,
direction.
then in that case, you are considering the incident ray at different positions.
Yeah.
Yeah. So I didn't still understand your confusion.
So, sir, there isn't just one generalized normal for a surface, right?
How can the definition of normal? Perpendicular, imaginary line perpendicular to the surface and of incidence. So this is the point of incidence for this ray. There will be point of the rays will be incident at different positions. So there will be different normals.
Okay.
Clear?
Thank you, sir. So, sir, at that exact point, the line that is perpendicular, right?
Normal, yes.
Yeah. Thank you, sir. Sorry, I was confused with this.
No problem. Now, factors affecting the angle of deviation. Now, angle of deviation is directly proportional to the angle of the prism. Is directly proportional to the refractive index of the prism. Because as the angle of the prism increases, the angle of deviation increases. As the refractive index increases, the angle of deviation increases. And
refractive index.
Can you explain the second point?
Second point, see, it is now for a particular ray. Okay, if this is the path. Now suppose I use a prism of greater refractive index, then the same ray would bend more. Isn't it, if the refractive index of the prism is greater?
Yes, sir.
So the angle of deviation is greater, and you know that angle of deviation is the deviation at the first surface plus the deviation at the second surface.
Yes, sir.
Refractive index increases, the bending increases. So both the deviations are increasing, so net angle of deviation also increases.
Yes, sir.
Yes, sir.
Clear?
Sir.
Yeah. And for now, for angle of incidence, it varies differently. Now, what happens for angle of incidence? If the angle of incidence is smaller, gradually the bending will change. So if I find out the angle of deviation, and I for different angle of incidences, if I carry out the experiment and find out what is the angle of deviation, I get the graph like this. Which means that if the angle of incidence is very small, this is y-axis is angle of deviation, this is angle of incidence. So correspondingly, this is angle of deviation. If the angle of incidence increases, what happens? You are coming toward lower value. You further increase, you come still towards the lower value. You further increase, you come to the lower value. When it is over here, it's here. When you go over here, then it starts increasing again. So what does it mean? That initially with the increase in the angle of incidence, angle of deviation decreases. Then it reaches to its minimum value called angle of minimum deviation. And beyond that, if I continue to increase the angle of incidence, the angle of deviation again increases. Are you understanding that?
Yes, sir.
Yes, sir. Sir, I have a doubt, sir.
Yeah.
Sir, will they ask graph for the exam, sir?
Yeah, they can ask.
Okay.
They can ask. They can ask. In fact, in your tomorrow's test, I have asked one question with respect to graph.
So, sir, to find the angle of deviation, we have to draw the graph, right?
No. It's not that from the graph you are supposed to find out the angle. There can be questions related to the graph.
Okay. So they will give us the deviation angle, right?
Yeah, they will give you the angle and they maybe give you the values on the graph, or the question can be asked in different ways. Like for example, now when the angle of incidence is very small, angle of refraction is also very small.
Yeah.
Okay. And from here there will be. So if I produce incident ray and emergent ray, I'll get deviation. As I increase this, correspondingly this will also increase. Correspondingly, this angle also changes. So accordingly, in this portion of the graph, till it reaches the minimum value, the refracted ray is towards the base. Now, when there is a minimum deviation, the refracted ray is a parallel to the base. And only in this condition, when there is minimum deviation, you have angle of incidence equal to the angle of emergence, and the refracted ray is parallel to the base at this position. Okay? And
yes,
and that is true if it is isosceles triangle or equilateral triangle. And beyond this, if my angle of incidence increases, then my refracted ray will be inclined upward inside the prism. And then it emerges outside. So in this part of the graph, the refracted ray inside the prism is bending towards the base. And as angle of incidence increases, the angle of refraction increases, so the ray starts moving upward. At minimum deviation, it is parallel to the base, and beyond that, it is inclined upward. And that's why initially the angle of deviation decreases, it becomes minimum, and then again it starts increasing. Is that clear?
Yes, sir.
Yes, sir.
Always remember, angle of deviation, if I draw a horizontal line here, that means corresponding to the two angle of incidences, you have same angle of deviation. Right?
Yes, sir.
Yes, sir.
So if this angle of incidence is say 45, okay, and corresponding to that, if I get angle of emergence to be equal, one second, let me draw the graph again to make it clear. So for some angle of incidence, let us say the refraction is like this, and then so if you have angle of incidence equal to 40 degrees, and correspondingly if you get this as 50, that means if you apply the principle of reversibility, if I produce this forward, this is your angle of deviation, this. This is the incident ray, this is the emergent ray, this is angle of deviation. But if I consider the principle of reversibility, this is the incident ray and this is the emergent ray, this becomes the angle of deviation and they are vertically opposite, they are equal. So whenever I get these two angles, if this is the angle of incidence, this will be the angle of emergence. If this is the angle of incidence, that will be the angle of emergence. Is that clear?
Yes,
Yes,
sir.
sir.
Two angles, you will get the same angle of deviation. The last point is it is inversely proportional to the wavelength of light. As I told you that violet has the smallest wavelength, so it bends the most. Comparatively, the other color bends the less. So now definitely the angle of deviation will be maximum for violet and minimum for red. Are these factors clear to you?
Yes,
Yes,
sir.
sir.
All these points I have already
Yes, sir.
Yeah, I have all these points I have already explained when it bends. So in this
Yes, red
portion.
and violet.
Yes, Mohammed.
I think so.
Excuse me, sir.
Yes.
Sir, I am not able to understand why the refracted ray is parallel to the base in case of minimum deviation.
Refracted ray is not necessarily parallel to the base. It will be parallel only in case of isosceles triangle and equilateral prism, not every triangle. Because, yes.
This is also not the condition for angle of minimum deviation.
No. It is only for isosceles and equilateral. Is that clear?
Yes, sir.
Yes, sir.
Yeah.
So, sorry, could you please repeat the conditions for the angle of minimum deviation case?
It is directly proportional to the prism, directly proportional to the refractive index. Then for angle of incidence, it initially decreases, becomes minimum, and then again increases. And the fourth factor is the wavelength of light. Shorter wavelength, it increases. Longer wavelength, it is less. Clear?
No, sir,
Yes,
I'm
sir.
asking that you tell now that angle of incidence is equal to angle of emergence in the case of minimum deviation. It is one condition, or there is any another condition also?
No, minimum deviation I is equal to E.
Okay, sir.
Yeah.
Sir, is it necessary for us to know these factors with the with the reference to this graph, or is it fine if we don't understand the graph?
You need to know the factors.
Yes, so the factors are fine, but like the graph, will there be questions with reference to the graph?
It can be asked. It can be asked.
So we have to be very clear with the graph, right?
Graph, yes, yes.
Okay, thank you, sir.
Sir, can you show example?
Can you what?
Examples of questions.
You want? See, suppose I can give you a horizontal line like this, and I will give you this angle and this angle. And in the diagram, I may give you same angle of incidence. Okay. And here, and correspondingly, the angle of deviation is marked. I can ask you what is the angle of emergence. So when that horizontal line cuts here, whatever is the other angle will be the angle of emergence. You should be able to identify that. Questions can be picked up from, can be designed anyway. I draw a horizontal line and I will give you this. And I may give you a triangle in which the angle of incidence is same as that of this. Corresponding to that, what is the angle of emergence? So you should be able to tell me that is the angle of emergence, whatever is the value given in the graph.
Sir, can outsiders also get the test paper?
That you ask Samir, I don't know. Now, these are the things which you are expected to know for different colors, which I've already spoken about while talking. So refractive index is maximum for violet, minimum for red. Frequency of violet light is maximum, minimum for red. Wavelength of violet light is minimum, maximum for red. Lateral displacement is maximum for violet and minimum for red. That means for violet, indigo, blue, green, yellow, orange, red is the sequence. The speed of light is minimum for violet, maximum for red. Angle of deviation is maximum for violet, minimum for red. And C stands for critical angle, which we are going to do later on, is minimum for violet and maximum for red. So,
Sir?
Yes.
So do we have to remember in context with each color all these factors?
Yes, that's what I'm saying.
Okay, sir.
Yeah. So your first. Now coming to now critical angle. Now when the light enters from denser to rarer medium, as the angle of incidence increases, the angle of refraction also increases. Correct?
Yes, sir.
So if this is the angle of incidence, let me show it to you like this. If suppose the light is entering some rarer medium to a denser medium. So if the angle, suppose the angle of incidence is the other side. So if the angle of incidence increases, correspondingly the angle of refraction, I made a mistake, denser medium. Okay. So if my angle of incidence increases, correspondingly my angle of refraction will also increase. So you keep on increasing. For some angle of incidence, you will have angle of refraction equal to 90 degrees. And for whatever angle of incidence this happens, this angle is called as critical angle. So critical angle is the angle of incidence in the denser medium for which the angle of refraction is 90 degrees. Okay. So it is the angle of incidence in the denser medium for which angle of refraction is 90 degrees. Now, what is the significance of this? Now, if my angle of incidence exceeds this, now if my angle of incidence go beyond this, then my refracted ray will no more, I mean, the ray coming into the medium cannot refract, but it comes back into the same medium and it obeys the laws of reflection. And this phenomenon is called as total internal reflection. Angle will be same as that of this angle. And almost 100% light energy is reflected. Maybe negligible amount is absorbed, but nothing is refracted. Otherwise, what happens whenever the light strikes, it enters into that medium, part of the light energy is reflected. But when the angle of incidence is greater than critical angle, the entire light energy is reflected, and this reflection is called as total internal reflection. It is the reflection in the denser medium when the angle of incidence is greater than critical angle. Normally, when the light enters, there is partial reflection, partial refraction, and partial absorption. When the angle of incidence is less than critical angle. When the angle of incidence is equal to critical angle, again there is partial reflection and there is refraction. And when the angle of incidence is greater than critical angle, there is not a slightest amount of light energy is refracted, entire light energy is reflected. And since almost 100% light energy is reflected, that's why this phenomenon is called as total internal reflection. Is it clear what is TIR? Total internal reflection?
Yes, sir.
Yes,
Yes,
sir.
sir.
Okay.
Sir, the critical angle, it happens when the light is refracted on the plane surface, right? On the surface.
Yeah, on the surface. When at that point it bends to 90.
Okay.
Otherwise, surface may appear straight, but there are going to be many ups and downs. But at that point, if it bends through 90,
yeah,
that is the critical.
So the 90 is between the normal and the surface.
Yeah.
Right, sir?
90 is between the normal and the surface, means between the refracted ray, because refracted ray goes along the surface, hypothetically. Because the ray goes along that path. And conditions for total internal reflection.
Thank you, sir.
The ray should have direction from denser to a rarer medium, and angle of incidence should be greater than critical angle of the medium. So these two conditions are required for total internal reflection. Under normal reflection, the reflection can take place for any angle of incidence, but total internal reflection will take place only from denser to rarer, and when the angle of incidence is greater than critical angle.
Excuse me, sir.
Yes.
Sir, I have a doubt. Like, suppose, according to the specimen paper of ICC, they had given 2 mark questions for which we have to select 2 options.
Yeah.
Now, suppose one of the questions is the phenomenon due to which a ray of light deviates from its path while traveling from one optical medium to another optical medium. One will be refraction. Can another option be total internal reflection?
But that option was given?
No, not in the specimen paper. I got this question from somewhere else. In that, they are given the options as dispersion, reflection, refraction, diffraction, and total internal reflection.
And what is the question?
A phenomenon due to which a ray of light deviates from its path while traveling from one optical medium to another optical medium.
No, then total internal reflection happens within the same medium, no?
But it's happening at the interface when it's happening from a denser medium to a rarer medium.
Yeah, but then the light is, they have said that light is entering from one medium to another.
Correct. But for these kind of questions, if it's for 2 marks, only one answer can be accepted.
That depends upon whoever is setting the paper. I mean, I don't think so, because if there are 2 marks, they will definitely expect 2 marks.
Yes.
Unless and until if there is a numerical and calculation is involved. Do that.
Yes. Thank you.
Now, relation between the critical angle and refractive index. Again, the derivation is not required. You need to know the relation. Mu is equal to 1 upon sine C. Refractive index is equal to 1 upon sine of critical angle. Okay, this relation you are expected to know. Okay. So factors affecting the critical angle, it is inversely proportional to the refractive index. Higher the refractive index, lower is the critical angle. Okay, because it is 1 upon sine C. Then it is directly proportional to the temperature. Basically, all factors that affect the refractive index will affect the critical angle, because with the change in the temperature, refractive index changes. So obviously the critical angle will change, because mu is equal to 1 upon sine C. So if the temperature increases, the refractive index decreases. Temperature increases, the refractive index decreases. So the critical angle will increase. Are you understanding? Mu is 1 upon sine C. So as mu increases, C decreases, or C increases, mu decreases. So with the increase in the temperature, if mu is decreasing, so the critical angle will increase. Right?
Yes, sir.
Yeah. And you are expected to know this. Critical angle of glass and refractive indices of these media. That's all, not beyond this.
Okay, sir.
Okay. Now coming to the applications. In fact, these are very important. Now, an object present in a denser medium, when seen through a rarer medium, appears to be raised. Now this is because when you draw this diagram, now I doubt they will ask you to draw the diagram. This year they cannot ask, but normally train the students to draw it like this. I asked them to take the reference of 4 lines, 1, 2, 3, 4 book lines, 1, 2, 3, 4. Surface of water will be over here, the image will be over here. Then from any point draw refracted rays. Below this point mark the incident ray and join that point to the incident rays. So how do you understand? So if a ray is coming from this point, when it strikes the surface, at the surface, it is entering from denser to rarer, so it will bend away from the normal. And when you produce them backward, they meet slightly above. Therefore, actually the object is over here, but you see its image over here. And this is what happens with every point on the base, and the base appears raised. Is that clear? So actually the ratio between them for water will be 3:4. This part is 3 and this part is 4. And you can, now many a times they ask you to draw a diagram of a coin raised in water or a stick partially immersed in water. So basic, first you have to complete this. Then you can draw a coin over here, you can draw the image over there. Now they may ask you to draw a diagram for stick partially immersed in water. So you don't draw coin, instead of that you draw stick over here. And from wherever it immerses in water, from that point to this point, you draw the dotted line. That is the image. So the basic diagram remains the same, but the attachments can change. Is the diagram clear? Shall I go ahead?
Yes, sir.
Sir?
Yeah. Yes?
Sir, are we not covering the different types of these refracting prisms?
Of course, they will come under applications. No?
Okay, okay.
Now we are doing the applications of refraction. After that, I am coming to the applications of total internal reflection.
Okay, sir.
Yeah. So, see, I am not going according to what the modules which are given in the textbook. I have divided, I have first finished the theory, then I am doing the applications. Okay, after learning the theory. Now, there is one more formula. The proof of this is not required. The refractive index is real depth upon apparent depth. So the questions can be asked based on that also. What is real depth? The depth from the surface of the object. I mean, the depth of the object from the surface of the liquid. Apparent depth is the depth of the image from the surface of the liquid. And the ratio between them will also give you the refractive index. So you have learned how many relation? Refractive index is equal to sine I upon sine r. You have learned the refractive index is equal to the ratio between the speeds. You have also learned the refractive index ratio between the wavelengths. And you have learned the refractive index is equal to 1 upon sine c. And you have learned the refractive index is equal to real depth upon apparent depth. Okay. Now there is one more formula. But even if you don't remember the formula, you can find out the apparent depth and subtract the real depth and apparent depth. Or otherwise remember the formula. Shift means this distance. The distance between the apparent depth and the real depth. The difference between the apparent depth and real depth is shift. And that is equal to real depth into 1 minus 1 upon refractive index. Okay, this formula can be applied to find out either real depth or shift or refractive index. Proof is not there again. Then an object seen through a triangular prism appears to be displaced towards the apex. Now, if this is a triangle and if there is any object and I'm watching it from this side, then I will not see the object. It will appear raised. Or if I'm watching it from this side, object is here, it will appear raised. With respect to this ray diagram, you will understand. Suppose the object is over here and there is observer on the other side. So the rays coming from the object, they refract towards the base because they bend towards the normal. And at the other surface, they are entering from denser to rarer. So they bend away from the normal. But in such case, when you actually draw the diagram, you actually draw the image first and then draw the emergent rays. Because what happens, you know, when you produce the emergent rays backwards, sometimes they go there, sometimes they go here, sometimes, so it depends upon at what angle you draw the bending. So it is advisable that vertically above, slightly inside, you draw the image and then join this point to this and this point to this by dotted line and produce the emergent rays. So the rays coming from the object, they refract and bend towards the base. So when eye traces the straight path back of these rays, the image of the object is formed over here. And what person sees, not object over here, but it will see over here. What you are saying is the image. Is that clear? Is it clear?
Yes, sir.
Yeah. Now the next application is, this is cancelled from your syllabus this year. Okay. During sunset or sunrise, we can see the sun, even if it is present below the horizon. Now, actually what happens? Now, surrounding the earth, there is atmosphere. Okay. And the layers closer to the surface of the earth are denser and away from it are rarer. Now, first of all, the horizon means, suppose a person is standing on the surface of the earth. For him, the horizon is where the plane arising from his eye level tangential to the surface of the earth. Here, the person will appear sky meeting the earth. So, if any object is present below this, the rays coming from this will be obstructed by the earth and therefore he cannot see it. Right? If there is the ship is moving up and it goes beyond the horizon, the rays coming from the ship are obstructed by the earth itself, therefore the person cannot see it because it is present on this slant portion of the earth. But when the sun is below the horizon, just during sunset and sunrise, then the rays which are coming from the sun, even if they do not have direction towards the person, but when they enter into the earth's atmosphere, they are moving from the rarer layers towards the denser layers, and therefore they start bending. And even if their initial direction is not towards the person, but due to refraction, they reach the person present on the surface of the earth, and the eye traces the straight path back of these rays, and you see the image of the sun over here. I have drawn only one ray, so number of such rays. And due to refraction, the image is formed above the horizon, and therefore you can see the sun even if it is present below the horizon. When you see during sunset and sunrise, if you see the reddish disk of the sun appears bigger. So when it is actually appearing bigger, it is already below the horizon. What you are seeing is the image. What you are seeing is the image. Now, the image also appears bigger. Why? Because the image is formed closer to the surface of the earth. Now, if you watch any object from a distance, the object appears smaller, but as the object comes closer, it appears bigger. So due to the same reason, the image is formed closer, and therefore, during sunset or sunrise, the sun appears bigger in size. Is that clear?
Yes, sir.
Then stars appear to twinkle. Now, same again reason. Surrounding the earth, there is atmosphere. The layers closer to the surface of the earth, they are denser, but they distant layers are rare. So if there is a star, okay, the rays coming from that, okay, the rays coming from that, till the time it is traveling in vacuum, it doesn't bend. But beyond that, when it enters into the Earth's atmosphere, it bends. Okay. Now, when it enters into the Earth's atmosphere, are these layers of atmosphere stationary? So actually, when the ray enters to your eyes at this angle, you are able to see the star over here. You are seeing its image. But the layers of air are not stationary. Therefore, the refraction which is suffered by the ray changes. So sometimes it comes at one angle, sometimes it comes at the other angle. And when I produce the ray backward, sometimes the image is over here, sometimes the image is over here, sometimes the image is over here. So the position of the image keeps on changing in the vicinity, and that gives you the twinkling effect. Variable refraction due to the variable refraction through the Earth's atmosphere, because these layers are not stationary. At night, if you watch the stars, okay, and you observe when there is a maximum breeze, you look at the star, the twinkling is maximum, because that time the mixing of the layers is maximum, and therefore variation with the refraction is maximum, and therefore you are focusing at one point where the star is seen. That image disappears and forms somewhere else, from somewhere else, and this gives you twinkling effect. Is that clear?
Yes, sir.
Planets don't twinkle because, first of all, the planets do not have their own light. And most of the time, when the rays come, reflected rays coming from the planet, even if they refract, the position of the image continuously overlaps. It doesn't shift so large because stars are at a greater distance, but whereas the distance of the planet is less. So therefore, they don't twinkle. Okay, because of their less distance and because they don't have their own light.
So, sir, this doesn't work for the moon, right?
A moon also is closer, no?
Okay.
It is also closer. It is not at a distance of stars.
Yeah.
That's the closest object, in fact, to the Earth. A person sitting on the opposite side of the campfire appears shimmering. You must have observed this. When you are at the campfire, a person sitting on the opposite side, you know that you find that person shimmering. Why? Because the layers of air rises upward, and when the light is passing through it, suffer variable refraction, and therefore the person on the opposite side of the campfire appears shimmering. You can try it at home also. On the gas, you keep utensil in which water is there, and once the water starts boiling, through the vapors you see the opposite surface. The opposite surface. Okay, that is because of variable refraction. Are you understanding? Even you must have seen the films which are shot in the afternoon on the Discovery Channel. In deserts, the screen appears shimmering. Why? Because of hot land, the layers of air is moving upward due to convection. And when the light passes through, it suffers variable refraction, and that's what the camera captures. And therefore, the screen appears shimmering. Is the application clear?
Yes, sir.
Even
yes, sir.
Commonly, if your car is being refueled, you come out of the car in the afternoon, and when the petrol is being filled into the car, you observe the surrounding region of the mouth of the petrol tank, where in your car the petrol is being filled. The surrounding region appears shimmering because petrol is volatile, so it continuously evaporates. So when you see through it, the surrounding region appears shimmering. Lines drawn at the bottom of the swimming pool appears hazy. Now this is in the morning, early in the morning, the swimming pool is not disturbed. You can see those black reference lines straight. But the moment someone jumps, the lines appear hazy, zigzag. Because when the surface is not disturbed, the refraction is relatively uniform. But the moment someone jumps, the surface is disturbed, and therefore the refraction varies. And therefore the lines appear zigzag because the rays come out at different angles.
Sir,
Yes.
Sir, does uniform refraction mean that it's normal, or
normal means surface should be straight, but there are always ripples on the surface of water.
Okay.
Are you understanding? So the surface is not absolutely plain in case of. But see, even if there are slight ripples, it's okay. At the most it will appear slightly shimmering. But someone jumps into the water, there are more big waves are formed on the surface of water, and that varies the refraction by large amount, and therefore the lines appear completely zigzag.
Okay, sir. So when it's normal, then when the surface is plain, then there's a very minimal amount of.
Minimum amount of refraction. So you may appear along the border, it is slightly shimmering.
Yes, sir.
Yeah.
Thank you.
So we finished the applications of refraction. Now coming to the, oh God. Where's the fourth one? Okay. Now the refraction through right angle isosceles prism. Someone wanted to know how to do the refraction through the prism. Okay. Now for this, you need to know the critical angle of glass is 42. Now right angle isosceles prism is also called as total reflecting prism because light on passing through the prism mostly suffer total internal reflection in most of the cases. And therefore it is called as total reflecting prism. Now you can use this to bend the light through 90 degrees. Now this is right angle isosceles prism. Now when you draw this prism, actually this here, so there is no question of drawing, but this length and this length should be equal. Now if I consider the ray incident normally, it will travel undeviated. Now the simple technique in completing this, that whenever you are completing the path of the prism, path of the ray through the prism, whenever the ray strikes the new surface, you do not complete the next part of the ray unless and until you calculate the angle at that point by using basic geometry or basic principle of reflection. Now this is 90 degrees, so linear pair is 90. Do you agree?
Yes, sir.
So if this is 45, this is 90. By angle sum property of triangle, this will be 45.
Yes, sir.
So when I draw normal at this point, it will give me the angle of incidence equal to 45.
Yes, sir.
Which is greater than 42 critical angle.
Yes, sir.
So the ray reflects. Again, it hits a new surface. So unless and until I calculate the angle over there, I will not complete the path. Now I know angle of incidence is equal to the angle of reflection. So this is 45.
Yes, sir.
So complementary angle is 45.
Yes, sir.
This is already right isosceles prism. So this is 45. 45 plus 45 will become 90. So what is this angle? Angle sum property of triangle, 90. Right?
Yes, sir.
Yes, sir.
So the ray travels undeviated. So the ray has direction this, but it goes along this path. That means it has turned through 90. Sorry. It has turned through 90. If I produce this ray forward, by how many degrees it has turned? 90.
90.
Yeah. So it is used in DSLR camera, refracting, periscope. This is the periscope diagram. The two right angle isosceles prisms are kept in such a way that all surfaces are parallel. So this hypotenuse is parallel to this is parallel to this, and this is parallel to this. Now when the rays strike the surface, now I have already explained it to you how the ray deviates through 90. So the ray travels, I have calculated the angle of incidence, it deviates through 90 degrees here. So it travels now. Since the other surface is also parallel, actually due to the first reflection, the first image is formed over here. Then the ray strikes the other surface. They travel undeviated. Again, like this, you get the angle of incidence equal to 45. The rays are reflected over here. Now, actually, this image which is formed at the first surface becomes the object for the second surface. So whatever is this distance, ideally that much distance behind the image is formed. So when you produce them backward, many a time the students show it vertically below this distance is greater. What you see in the periscope is only this image, not this image. You see this image. And we prefer periscope because it gives you the image because of total internal reflection. The image is and clearer. And that's the reason we do not prefer mirrors, but we always prefer prisms for periscopes. Is that clear?
Yes, sir.
Okay. The next application is the deviation through 180 degrees. Now, in this case, when you draw the prism, there is a technique. You draw the base, mark the midpoint. Then vertically above, mark a point. Suppose I have taken this as 8. If I mark midpoint, this will be 4 and this will be 4. So vertically above this, I will mark a point at a distance 4 centimeter. And then I will, otherwise, like I have seen the student drawing the prism and it looks like isosceles prism, it looks like equilateral. This will exactly be right angle isosceles prism. Okay, if you have to draw the diagram.
Sir, I'm sorry to disturb you.
Yeah.
But this one that you're telling right now, so we should, this is the angle of
So
deviation should be
now
180.
this time they will not ask you to draw diagram.
Yes, sir.
Diagrams you need to know because they may give you different sequences and say, put the sequence.
Yeah.
Diagrams.
Yes, sir.
Yeah.
So this topic right now, what should be 180? Sir, I'm not really understanding. Should it be the angle of deviation 180 or
Yes, right angle isosceles prism which can be used to turn the light through 180. That means deviation is through 180.
Okay. So all of these cases are the angle of deviation is equal to whatever number. Okay. Thank you, sir.
Sir, excuse me, sir.
Yeah.
We use these 90-degree deviation reflecting total TIR prisms in periscopes to give a clear image and what kind of image?
Clear and brighter.
Brighter, okay.
Internal reflection. Otherwise, in mirror there is more what do you call
dim. It will be dim.
Yeah.
Yes.
So, sir, for this examination, we have to tentatively know these diagrams, right? Not
Yes.
Thank you.
See, 1 second. Let me tell you. You learn for future. Don't learn for the exam. That is what. Of course, towards the exam you have to learn for the. But it is always better you understand. So like at any point of time, like even if the question is twisted, yes, you will be able to deal with that question. Okay, that is what I prefer.
Yes,
always prefer. Now the ray strikes the surface normally, it travels undeviated. As I told you, when it strikes the surface in the denser medium, you don't proceed unless and until you calculate the angle over there. Now this ray strikes the surface normally, so this angle is 90. This is 45. So angle sum property, this is 45. So angle of incidence is 45. Or I can calculate in terms of this angle, it doesn't matter. This is 90, this is 45, so this is 45. So complementary angle 45. Is this clear?
Yes, sir.
Yes.
So angle of incidence is greater than critical angle. So the ray will reflect, making angle of reflection equal to 45. So if this is 45, complementary angle 45, this angle is 90. So by angle sum property, this is 45.
Also be 45.
So when I draw normal, this angle becomes 45 angle of incidence.
Yes, sir.
Which is greater than critical angle. So at this surface, the ray has already turned through 90. So once again, it will turn through 90 here. Again, it strikes this surface. Angle of incidence is equal to the angle of reflection. So 45. Complementary angle 45. So you get 45, 45. So angle sum property 90. So it comes out undeviated. So it turns through 90 at this surface, again turns through 90 at this surface. So therefore deviation through 180 degree, because it is going along this direction, but comes along in the opposite direction. But at the same time, the ray coming from A comes out from the other side. The ray coming from B comes out from this side. So there is a lateral inversion. Right becomes left, left becomes right. Is that clear?
Yes, sir.
So what you need to know that this kind of deviation is used in binoculars and projectors. Okay.
Yes, sir.
They will never ask you to show the images, but I'm telling you, due to the first reflection, the image is found over here. Due to the second reflection, the image is found over here. So what you see from here, the image won't be over here. The image is actually over here. Okay.
So, sir, the eye is the image, right?
Here the eye position is there.
Okay. So actually, I thought that in the beginning, when you were showing this diagram, I thought that the light will escape from the left side because it's touching that one. No, sir.
Is it clear? But is it
Yeah.
clear? Yeah.
Yes, sir.
Now in the third case, inversion without deviation. Now in this case, right angle isosceles prism, if there is any object present on this side, and if you watch it from this side, you will see this object down. Why? Now imagine the rays coming from here. When they strike this surface, and they strike the base. Since I have taken the rays which are parallel, so their angle of incidences will be same, so angle of refraction will also be same, so both the rays are parallel. Now here you should know that when this ray strikes the lower surface, angle of incidence will always be greater than critical angle. You cannot calculate it, but you can prove it. So angle of incidence is greater than critical angle, so the ray will reflect from here. So
Yes, sir.
incident rays are parallel, after reflection they will be parallel. And whatever is this angle, if you use the geometry, you can prove these two angles are also equal. This and this with the normal. Not this is 45 is this. With the normal, these angles are equal. So apply the principle of reversibility, so you will get the rays parallel again. So you will see it from here, but if you observe the ray coming, suppose this is the person standing, so ray coming from his head comes out near his feet, and the ray coming from his feet comes out from the head. And due to this, you see the object present on the opposite side inverted. So this is inversion without deviation. Is that clear?
Yes, sir.
Excuse me, sir.
Yeah.
Sir, how could we prove that angle of incidence is greater than critical angle?
Let us say this is the prism. Now I have drawn this ray. Now tell me one thing, if this is a surface and the rays are coming from this point, if the rays strike over here, when the rays strike further, when the rays strike further, what can you say about the angle of incidences which they form on this surface? It goes on increasing.
Yes, sir.
Okay. Now imagine the ray is incident along this surface, along the normal. Correct? So at the lower surface, it forms angle of incidence 45. Yes. If the ray is incident along the normal, at the lower surface, what angle of incidence it forms? This is 90, this is 45, this is 45. So complementary angle 45.
Yes, sir.
So the ray will reflect because 45 is greater than critical angle, right?
Yes, sir.
Yes, sir.
Instead of ray traveling along the normal, it makes certain angle of incidence. So obviously there will be certain angle of refraction. So from this point, the ray is striking further. Use this reference. Will this angle be more than 45? Yes or no?
Yes, sir.
Yes, sir.
So if the ray is incident normally, that time when the angle of incidence is 0, then also the angle of incidence at the lower surface is greater than critical angle. So if it is going to make some angle of incidence, the rays are going to refract more on the right hand side. So the angle of incidence is going to be greater than that. Huh?
Okay, sir.
Got it?
Yes, sir. Thank you, sir.
Yeah.
So all of these cases are the angle greater than the critical angle, right?
Yeah, total internal reflection takes place only when angle of incidence is greater than critical angle. No?
Yes, sir. So I thought critical angle was 90.
What is definition of critical angle?
Actually, in the previous page, that's
1 second. Which previous page? Let us sort it out your difficulty. Which is 90? This is not critical angle. Critical angle is the angle of incidence when the refracted ray will go along the surface. Make angle 90 degrees. And that will happen if the rays strike the surface at an angle of incidence equal to 42 for glass. But it is more than that, so ray will reflect. Na?
okay. So, yeah, thank you, sir.
So is this clear? The inversion without deviation?
Yes, sir.
Okay. Now, this is actually the laser. I always show it to the students in the class. See, this is the deviation. Can you see this is the prism? Here, it is kept in the dark. So the laser, it is deviation through 90. Okay. Then it is deviation through 180. Then there will be inversion without deviation. The ray is coming, strikes, goes from here. So now if it is taken up, the ray will come from down. Afterwards, he will move this accordingly. If the rays are coming from the upper portion, they will come out from the lower portion. They are coming from the lower portion, they will come out from the upper portion on the other side. Did you see that? It's coming out. So if there is any object, the ray coming from the upper portion will come out from the lower. The ray is coming out from the lower portion. After refraction, they will come out from the upper portion. Clear?
Yes, sir.
Okay. Now TIR through 30-60 prism. Now this is 30-90-60 prism. Now when the ray strikes the surface normally, it travels undeviated. Again, my instruction is the same. When the ray strikes a new surface, by using basic geometry and laws of reflection, calculate the angle without which you will not proceed further. Now this is 90, this is 90, linear pair. So it forms a triangle over here. This is 30, 90. So this will be 60. Angle sum property of triangle.
Yes.
So draw normal at this point. So if this is 60, complementary angle is 30. Now ask the question yourself, is this angle greater than critical angle? Critical angle of glass is 42. So the ray would refract away from the normal because denser to rarer. Now, if the ray strikes from this surface, all the rays coming from this surface will refract outside. If the rays are coming from this side, travel undeviated. Striking the new surface, my job is to find the angle over there. So this is 90. This is it clear? 90, vertically opposite. This is 60. So complement angle sum property, this is 30. So if I draw normal, this angle will become 60, which is greater than critical angle. Critical angle for glass is 42. Now the common mistake the students make, they draw this angle over here, straight line, and show coming out. But you should understand, if the angle of incidence is 60, angle of reflection will also be 60. No?
Yes, sir.
So if this is 60, this will be 30. This is also 30. That means this whole angle is 120. Right? This is 60. Angle of incidence is equal to the angle of reflection. Complementary angle is 30. So when the rays strike this surface, you get this angle 30. You get this angle 30. So angle sum property, this whole angle is 120.
Yes, sir.
How can the rays strike normally? So many a time the students straightway draw without calculating the angle and then they go wrong. So you draw this. This is 120. So when I draw normal at this point, from 120 subtract 90, remaining angle is 30.
Yes, sir.
So it's less than critical angle. So at this point, the ray is entering denser to rarer. So it will refract away from the normal. Is the path clear?
Yes, sir.
Okay, now the ray is incident on the hypotenuse surface. The ray is incident on the hypotenuse surface. So there are two possibilities: hypotenuse surface having direction through this surface as well as through this. Now I am taking through this surface. The ray is incident normally, travels undeviated. This is 90, this is 30. What will be this angle? What is this angle? Come on, it's not a difficult question. This is 90.
So 30.
How 30? 90, 30 will give you 1.
60.
60.
60, sorry.
How 65? 60 degrees. Angle sum property. 90, 30. Subtract the addition of these two from 180. So that will give you 60. So when I draw normal, the angle of incidence will be 30. Probably, I don't know, you must have told me this angle. I am asking you this angle.
Yes, I got confused.
So this is less than critical angle. So the ray would refract, bending away from the normal. But what if the ray is incident and after producing hits this surface? Now this is 60, this is 90. So by angle sum property, this angle is 30. 60.
Yes, sir.
Subtract it from 180, you will get this 30. So when I draw normal at this point, since this angle is 30, I will get this angle as 60.
Yes, sir.
Critical angle. So total internal reflection takes place. So angle of incidence is equal to the angle of reflection. So that is 60. So complementary angle will be 30. This is 90. This is 30. So this angle by angle sum property of triangle will be 60 degrees. And since this is 60, so complementary angle will become 30, which is less than critical angle. So here the ray enters from denser to rarer, bending away from the north. Are this clear?
Yes, sir.
Are the diagrams clear?
Yes, sir.
Someone had asked, I don't remember who, but someone had asked this. Is that clear to you? Who had asked this question before, sir? Are you not going to do the prisms?
Yes, sir.
Yeah, okay. Okay. Now, an empty test tube, other applications of total internal reflection. An empty test tube, when obliquely placed in a beaker, okay, filled with water, appears silvery when viewed from the top. Now, the rays diagram is not important in this case. The rays coming from the side. Now, there is water and inside there is air. Because total internal reflection can take place only from denser to rarer medium. And some of the rays hitting from the side has angle of incidence greater than critical angle, and these rays will reflect upward. So when you are seeing it from the top, you are receiving those reflected rays, and due to this reflection, the surface appears silvery like a mirror. But if you pour water inside, the effect will disappear. Why? Because the condition of total internal reflection is not satisfied. The ray is no more traveling from denser to rarer. There is water inside after that. Okay. So if the test tube is empty, it will appear silvery, but if it is filled with water, the silvery effect disappears, because then total internal reflection does not take place. Is the application clear?
Yes, sir.
Okay. Now, diamonds glitter. Now, basically, the diamonds have very high refractive index and small critical angle. So small critical angle means the rays strike the surface, the chances of angle of incidence, please pay attention. When the critical angle is smaller, the chances of angle of incidence being greater than critical angle are more, because the ray can easily exceed smaller angle, critical angle. So when the ray enters the diamond, see, the more the surface is to the diamond, the more is the glittering of the diamond, because you provide so many surfaces for total internal reflection. When light enters inside the diamond, it is as good as it keeps on reflecting over the number of surfaces. It is as good as the light is trapped inside. It keeps on reflecting continuously, because the light may strike one surface. So when the light hits at any surface, let us say here, it refracts. Angle of incidence exceeds critical angle. Here again, it exceeds critical angle. Reflects, and it keeps on happening. At some point of time, when it is less than critical angle, it may come out. But otherwise, it will keep on reflecting inside. So that's why the more the surface is, more is the glittering, more is the cost of the diamond. Okay. So due to high refractive index, small critical angles, once the ray enters inside, they keep on reflecting. And since they keep on reflecting, you know that due to reflection, the surface appears shiny. And that's why the diamonds glitter. They even glitter in the dark because they already have trapped light inside. So in the dark, even if there is no external light, but the trapped light sometimes causes, it comes outside and it causes the glittering of the diamond. Is that clear?
Yes, sir.
Okay. Now, inner surface of the glass, this you can do it now also. If you have a glass nearby, fill it with water and hold it above your eye level and look at the inner surface. The inner surface will look like this, like a mirror. See, I have held my finger and I can see the reflection of that in the upper surface. Because when it is above your eye level, the rays coming from the side hit the inner surface of water and the angle of incidence exceeds critical angle and these rays reflect your eyes. If your eye position is above, you will not receive the reflected rays. And therefore, when the glass filled with water is held above your eye level, the inner surface looks like a mirror. Is that clear? Is it clear?
Yes, sir. Yes, sir.
Okay. Now, mirage. Mirage is false appearance of water due to total internal reflection. Now, in deserts, what happened? The land is very hot. So the layers of air absorb heat from the ground and they are comparatively rarer as compared to the above layers. I'm not talking about the entire length of the atmosphere. This is certain range of layers near the surface of the earth. So, yes, so when the light rays are moving towards the ground in the deserts, they are actually moving from denser towards the rarer layers. Do you agree with this?
Yes, sir.
And as the ray goes to the next layer, if you imagine, draw normal, the angle of incidence will keep on increasing. Draw normal, this angle will be greater than the angle over here. So as it is moving towards the ground, at every next layer, the angle of incidence keeps on increasing. So somewhere near the ground, angle of incidence exceeds critical angle and the rays reflect. And when you receive those rays, due to the reflection, apparent intersection, wherever the rays are coming from, you get the image. It may be the image of the sky. And the very fact you see due to total internal reflection, the image of the sky, you feel that there is water present. Because when do you see the image on the ground? When there is water. And plus these layers are also moving continuously upward. So this ray which reaches the eye of the person is not coming with steady refraction. It keeps on changing. So therefore, this image keeps on shimmering and that gives you the optical illusion. You feel that there is water present. So when this person tries to walk closer to that water, the image is seen over here. When the person walks closer, what happens? The rays coming from this region suffer total internal reflection behind him. So
yes, sir.
This image, will you see this image? The image is seen because you are receiving the rays. But if he is not receiving the reflected rays, why will this person see the image? Instead of that, the rays coming from the distant position will suffer total internal reflection and the same effect will go further. And this will keep on happening. You keep on walking towards the water, the effect keeps on moving away. And this false appearance of water due to total internal reflection is called as mirage. So mirage happens because of total internal reflection. Is that clear?
Yes, sir.
Yes, sir.
Yeah. Then optic fibers. It's a very important application. Optic fibers, your net, okay, GeoNet has optic fibers because they transmit energy continuously due to total internal reflection. Therefore, over long distances also there is a less loss of energy because during total internal reflection, almost 100% energy is reflected. So optic fiber transmit this bold points are very important. Questioning can be done on that. Optic fibers transmit light energy over long distances without loss of energy due to continuous total internal reflection. Is that clear?
Yes, sir.
Yes, sir. Yes, sir.
Okay. See, optic fibers are used in the computer data cable. They are used in telecommunication cables. In endoscopy, endoscopes also they use. Okay. So it has many applications. So you should know this and some of the instruments in which it is used. Anything else you want to ask? Anything else?
Excuse me, sir.
Yes, sir. The equilateral prism.
Yeah.
The 60 degree prism in that TIR, the deviation is it 60 degrees or 120 degrees? Because I'm facing a lot of different.
Let us see. Now, see, I'll tell you one thing. Once I've told you the technique, you should try to apply it. See, application is very important.
Yes, sir. With that, I have got 60 degrees as.
1 second. Let us see. Na? Suppose the rays strike the surface normally. Okay.
Yes, sir.
So let me produce this ray further. But the ray will reflect from here. Now I draw. Now this angle is 60. This angle is 90. This angle is 30. So angle of incidence is 60, which is greater than critical angle. So the reflected ray. So this angle is also 60. So this angle is 30. Correct?
Yes, sir.
And this is already 60. So the ray hits normally.
Yes, so it will come out.
So it will come out. Now, this is the direction and the ray goes along this path. So this is the deviation. Huh?
Yes, so it's 60.
60, 60, 120 plus 30, 50. This is the straight line. So the total sum of all the angles should be 180.
Yes.
Get angle of deviation to be equal to 60 degrees. No?
60 degrees, yes.
Correct? That is correct what you got, 60 degrees. Anything else?
No, sir.
Excuse me, sir.
Yes.
So, like, I just want to ask this question. So, like, what is the difference between refractive index and absolute refractive index? Like in a textbook, like the word absolute is not written actually.
I will explain. Wait, 1 second. Now, suppose A mu G. Air, A stands for air, and G stands for, let us say, glass. I can also find out W mu G for water, and G stands for glass. So this is refractive index of glass, but with respect to air. This is also refractive index of glass, but with respect to water. Correct? So when I can find out refractive index of any medium with number of other medium, so there could be communication confusion. If I say refractive index of glass only, I don't specify the other medium. So it is the international convention that the other medium assumed is air or vacuum, and this refractive index is called as absolute refractive index. When you consider the refractive index of any medium with respect to vacuum, that is absolute refractive index.
Okay. Yes, answer. Like I actually had another doubt. So, like in the factors affecting the angle of deviation, over there, like how does the thickness of the medium affect the angle of deviation? Can you just explain it again?
Angle of deviation in the prism, or which one?
No, sir. Like yes, one second, sir. Sir, like in the
Rectangular glass block.
Yes, sir.
Okay. That is a lateral displacement you want.
Yeah. Lateral displacement. I'm sorry.
Okay. Now suppose the ray strikes here. It bends and comes out parallel. Let me produce. This should be dotted, huh? Imagine. right? So this is the lateral displacement. Now let us say my prism does not have this much width. It has width till here. Then obviously this ray will not change its medium over here. It will change the medium at this point. Because width of the block is now this much, na?
Yes, sir.
So from here it will come parallel.
Okay. So like more
The lateral displacement is this much. But when the width is this much, the lateral displacement is this much.
okay. So like when the width is more, so like basically the light will reflect 2 times. Right? The light will reflect.
No, not 2 times. This is a separate condition and this is a condition. This is one block and it could be another block. The light doesn't deflect 2 times. When you suppose angle of when the refraction, you study the lateral displacement, due to less width, the lateral displacement will be less. But with same angle of incidence, when it emerges out due to greater width, the lateral displacement would be greater.
Okay. Yes, sir. This is last doubt. Doubt.
So you ask as many doubts. You should.
Yes, sir. Thank you so much, sir. Sir, so like they say the frequency of light, like it depends on the source. The frequency of light depends on the source.
Depends on the source.
But the wavelength is the same. Like it remains the same. Like for example, if you take red.
No. Frequency remains the same. Wavelength can change as it moves from one medium to another.
Okay. Sir, but like
see, last year you have learned sound.
Yes, sir. Yeah.
In that you learn V is equal to F lambda.
Yeah.
So in that you have learned the frequency depends on the source. So if the wavelength increases, the velocity increases. That's
so like how does the frequency depend on the source? Like
how does
the more no like how does the frequency of light depend on the source? Like
okay,
or in simple terms, like how can we get to know if the light is more frequent or less frequent? Like
light is more.
Brightness.
See, I can tell you 1 second. At this stage, I can with respect to a mechanical wave. Let us say you have a string in your hand. Now, when you move your hand once up and down, you will get 1 pulse. Correct? And that will remain the same in whatever time this pulse has formed. Along the string, it will travel with the same frequency. But if I start moving my hand up and down with a different speed, then the frequency will change. So once a wave is formed, as it is producing further, it will move at the same frequency unless and until at the source itself its frequency is changed.
Okay, so like basically the frequency depends on time.
Of course, F is equal to 1 upon T. You have learned that.
Okay. So like then what about the wavelength? Like the wavelength, like it always remains this thing, right? Like the wavelength, like for example,
Okay, one second. Yeah. Frequency is number of such waves formed in 1 second. Let us say if I say this is 50 hertz. That means 50 vibrations in 1 second. Right? Right?
Yes, sir. Yeah.
Now, wavelength is from here to here. Let us say wavelength lambda is 20 centimeter. Now, if you have learned the waves, understood the waves proper, when any particle completes one vibration, in that time, the wave will reach over here. That means during one vibration, the distance traveled by the wave is 20. So one vibration, the distance traveled is 20. So during 50 vibrations, how much is the distance traveled? So that will be 50 to 20. Right?
100. Yeah.
No, I'm not interested in. I'm not interested in the multiplication. During 50 vibration, the distance traveled is 20. 50 into 20.
Yeah, correct.
Now 50 is the frequency which are completed in 1 second. So that means whatever is the distance traveled during 50 vibration is the distance traveled in 1 second.
1 second. Okay. Like that.
Correct?
Yeah, yes.
This is the distance traveled in 1 second. So 50 is nothing but the frequency and 20 is nothing but the wavelength. So distance traveled in 1 second, you call it as frequency.
Yeah, the distance. Yeah, you call it.
So V is equal to F lambda.
Oh, so like that. Okay.
Clear?
Oh, yeah, yes, I understood. Thank you so much, sir.
Excuse me, sir.
Yes.
Sir, as you have told, in case of refraction, there is partial reflection, partial refraction. In case of 90-degree, it bends undeviated. Sir, in that case, is there partial reflection?
Of course. Of course.
Okay, sir. And sir, if we are not given the refractive index values, we will take the decimal values for numericals or fraction values.
Fraction. If you are using the first value for the next, but actually that problem will not occur this year because you are not writing the paper. You are going to attempt MCQ.
But sir, if we have to find the answer ahead to solve a numerical,
then you have to use the values which are given. You cannot take values of your own.
okay, sir. And sir, if we are given the incident ray, suppose in subjective exams, if we are given the incident ray and we have to draw the refracted ray, we will simply draw by following denser medium and rarer medium. Or
yes, no exact measurement of the angle. No.
Okay, sir.
You will not have numerical based on mu sin I upon sin R.
Okay, sir. And sir, as you said about the refractive index, as you were saying, medium A refractive index G. Sir, we will not say it GA. I'm having confusion in that.
You will not say GA means I didn't get it what you're saying.
So for example, we are writing refractive index of glass with respect to air. So we are writing A on left side and G on right side. So sir, I'm having confusion that we will spell it as A refractive index AG or GA.
In that sequence, you read from left to right. So in that sequence only you go A mu G, but it is the refractive index of glass with respect to air. When I say A mu G, it's the refractive index of glass. This medium's refractive ability of this medium to bend the light. If I say G mu A, it is the ability of air to bend the light when the light is coming from glass.
Okay, sir.
When you speak it, you call it as G mu A, but it is the refractive index of latter with respect to first.
Okay, sir. And sir, could you please again show the diagram that you showed while explaining angle deviation 3 cases? Angle of minimum deviation 3 cases.
Okay. Where was it? I think in this. You're talking about this, na? In the first portion.
So the 3 diagrams that will come on the side.
So in this part, the rays are bending downward. This will correspond to this. And this part will correspond to the ray having direction upward.
So could you please repeat?
PQ in when the ray and with the change in the angle of incidence, angle of refraction is changing. For smaller angle of incidence, you get this part of the graph.
Okay, sir.
When it reaches to minimum deviation, it will correspond to this. And when you increase the angle of incidence further, the angle of incidence is increasing. Here is less, it's more, it is still further. So now the ray will go upper because angle of refraction will also keep on increasing. Now here it is less, here it is more, it is still further.
Okay, sir. Thank you, sir.
Yeah.
Sir,
Yeah.
so sorry.
Yeah. Yeah.
So
Say.
the total internal reflection in a prism, that part, I understood how the light was deviating within the prism. But when they're saying that to deviate a ray of light through 90 degrees and through 180, what do they mean by that? I'm not understanding that part.
Deviated through 180, na? See, what is the angle of deviation? It is the angle between the incident ray and the emergent ray. Correct?
Oh, yes, sir.
1 second. I'll show it to you.
Yeah, sorry, sir. Actually, this part was a bit confusing. The rest of the chapter was clear. This part was like a little bit.
Keep basic definition in your mind.
Yeah.
What is the angle of deviation? Direction, incident ray and emergent ray. So you produce the incident ray. What is the angle between them?
90.
90. So deviation through 90. Produce the incident ray further and the emergent ray. Angle is 90. This is the application of that. Now deviation through 180. This is the incident ray.
Yeah.
So incident ray is along this path and emergent in the opposite direction. When will this happen? Unless until the ray turns through 180, can it go in the opposite direction?
No, sir.
So if the ray is traveling in this direction, if the ray is traveling in this direction, it will go in the opposite direction only after turning through 180, na?
Yes, sir. Yeah.
Got it?
Yeah. Thank you, sir.
Yeah. Anything else?
Sir, like when this light ray strikes this, strikes the surface, it will it's total internal reflection because it's more than 42, right? If it's less than 42, then it will go out of the prism, right?
Yes, yes, yes.
That's the
It's
only
not,
main rule, right?
listen. It's not that there are only total, along this there could be refraction also. So suppose there is an observer over here, there is an observer over here. He will see both the images. The person will see reflected image and that observer can see the refracted image. Whichever the refracted rays reaches, whichever observer, he will see the image formed due to refraction. And this observer will see the image due to total internal reflection. So we are showing the diagram only how total internal reflection is. These are not the only rays which are coming from the object.
Okay.
Yeah.
Okay, thank you, sir. And but that one, when we're seeing that from another point of view, then what you said, that will be applicable, right?
Yeah. Now, for example, there are another rays which are hitting the surface and they are not normal, but they will refract and then come out from this.
Yeah.
So they will see the refracted image. They will see this object slightly above.
Okay. Thank you, sir.
Yeah.
But if we really want to like find this by ourselves, like you just said, when somebody else asked a question, that we should try this by ourselves. Like,
yes, that's the best way of learning.
Yeah. Thank you, sir. So for that, this condition must be met, right? 42, if it's less than 42, then it will go out.
That is 42. There are different classes. The angle of deviation, critical angle changes now with respect to material.
Yeah, right. Thank you, sir.
Okay.
The wavelength will be always taken in meters, no?
SI unit is meter.
So there's one doubt which I came across in MCQs, which is little, it's like when a flashlight is switched on, It's about conversions. It's like when flashlight is switched on, the electrical energy, is it first converted to light energy and then to heat energy, or heat energy and then to light energy?
Flashlight is heat to light, I think.
Heat to light.
Yeah.
Okay.
But Surjit, still, I'm not sure. You need to check next time. Just remind me. Flashlight is heat to light, but I think so. 99.9, but I'll confirm.
Sure.
Yeah. Anything else? If there are no doubts, all the best, children. I am happy that you are, you are communicating. This is where the learning takes place. Okay. If you are solving your doubt, there is communication, two-way communication. Okay. And I'm sorry for those outside people who are coming in between and continuously using foul language, but it was beyond my control. And in fact, it distracted also me in the beginning. If there are students, those who are interested, then, you can teach properly, but then this was unexpected. I'm sorry for that.
Sir, I am also sorry from my behalf also, sir, that the real meaning of this session was that every student should get benefit from this.
Yes.
And the best teacher should reach out to the remotest student, and
Yes.
the best teacher should teach each and every student. Sir, can we please cover up the doubts from the YouTube as well? Like the students who are literally watching us live on the YouTube have been posting doubts.
I will, but not at this stage, because what happened, the workload is so much.
Correct.
And in a short span of time, there are so many things, expectations, because see, every year my entire material is in the form of normal questions. To convert them into MCQ, it takes a hell of a time. I'm telling you, for 20 marks, I spend one day.
Correct. Sir, just a one or two, sir. Like they have already put
No,
it
what
up
I
in the
will do
chat.
from that, whichever are pertaining to the examination point of view, I will take them first.
Sure, sir. I'll tell you, like you decide whether is the doubt relevant or not, because you are the subject expert.
Yeah.
Sir, Supratim Roy asks, deviation equals to I plus E minus A. Then how is the
deviation equal to
I plus E minus A?
One second.
Then
I plus E.
Sir, let me put it in the chat box so that you will get fair idea.
No, you tell me. I'm sharing the screen. C minus A.
Yes, I open bracket, I plus E, bracket close, minus A. Then how is the angle of prism A directly proportional to the deviation?
Because I and E, see, what do you call? See, when suppose angle of incidence is 40 degrees and angle of emergence is 50 degrees. So their addition will always remain constant. Addition of I plus E will always remain constant. Whatever is I, correspondingly this. So if this is the angle, this will be 40 degrees. So the change will take place with these two only. Na? If this is constant, I plus E.
Perfect. It might have helped, sir.
It's like this. This is I, and then this is E. So if this is 40, then this is 50. So if you take angle of incidence, 50, angle of emergence will be 40. So this will always be constant. No?
Perfect. Sir, can we have is this doubt also relevant? Like angle?
No, it won't be asked for ICSE level 101%.
Perfect. I hope, sir, like this doubt might have been resolved.
Yeah.
This Chimera Init is a girl or a boy. I don't know what the gender is actually. He or she is asking that can the angle of incidence be equal to the angle of deviation as vertically opposite angles?
Angle of incidence be
equal to angle of deviation.
I plus E is equal to A plus. Yeah, there is. There is possibility.
Okay.
There is possible, no problem. I don't think so. Why it should not be?
Sure.
Yeah.
Just a last doubt, like as we have time restrictions as well, I'll check whether like if there is a relevant doubt. Okay. So like, is this a relevant? Like, can momentum be hidden to human eyes, like how kinetic energy can be hidden as heat?
No, not pertaining to this.
Not pertaining to this.
Yeah.
Okay. Okay, guys. I hope like the YouTube people also learning from this. By if any chance, if anyone has like, if anyone is willing to subscribe to the course, like if anyone wants to study hard, please visit to the Roughbook app. If you have an Android phone, download Roughbook app from Play Store. If you have an iPhone, download Class Plus app from App Store. Enter the organization code as OINIO, and you will be redirected to the Roughbook app. Serve the store option, whichever course you want to get yourself enrolled into, whichever course suits you the best, go and get yourself enrolled, as we are dealing like into like the price is very reasonable. Like I am just asking for just the price which we would be able to survive. We have a office team, we have office, we have teachers, we have AWS servers, then all these technical glitches have to be taken care of. Whatever we are charging, guys, is literally zero. We are keeping the amount of profit equal to null. So there is no amount of profit, there is no way that we could make money out of this. And perfectly what I'll do is, like, if by any chance if you face any difficulties, I'm putting my number into YouTube live chat as well. It's 91529583335. Reach out to us at any moment. We are always available to you. And whenever you are stuck anywhere with regard to your studies, 9th and 10th ICSE students, the Roughbook app is there to help you out. Sure, sir. I hope, sir, we are good to go. And yes, is there anything else that you need to add on, sir?
No, thanks.
Perfect.
Thank you for
it. Was literally nice, sir. The session was simply terrific. The way you taught was simply stunning, sir. The pace of the session was too good. Thank you, sir, for being here with us on our platform. It means a lot, sir.
Thank you. Thank you very much. Good night, all of you students.
Thank you, sir.
Yeah.
Thank you, sir.
Okay, good night.